Have you ever wondered what it would feel like to be staring into the heart of a galaxy, only to find it staring back, erupting with energy, spitting matter at speeds so fast it shreds the fabric of reality itself? There are forces in the universe that don't just defy logic, they obliterate it. Black holes that consume stars like popcorn, galaxies that collide in slow-motion cosmic dances, and then, there are the ultra-fast outflows. Buried deep in the hearts of galaxies, lurking behind swirling clouds of cosmic dust and light, there exists something stranger than fiction, more violent than imagination, and far more real than we're comfortable admitting. These are not just high-speed winds. These are torrents of matter blasting out of active galactic nuclei, regions so bright and volatile, powered by black holes so incomprehensibly massive, that even light itself bends and quivers in their presence. But before we continue, subscribe to the channel so you don't miss any of these videos. Let's get back to the video. Ultra-fast outflows, or UFOs, as scientists call them, aren't UFOs in the way Hollywood would have you believe. No little green men. No flying saucers. Instead, these are colossal, relativistic winds, blasting away from the vicinity of supermassive black holes at a significant fraction of the speed of light. And they are doing something truly bizarre. They're sculpting galaxies. They're reshaping the very structure of the cosmos. They are cosmic sculptors, carving the fate of billions of stars with invisible hands made of radiation, plasma, and speed. But here's what they don't tell you in textbooks or documentaries. We don't fully understand how they work. We see them. We measure them. But we can't yet explain them completely. And that mystery might just hold the key to understanding how galaxies, and perhaps life itself, formed and evolved. So what are ultra-fast outflows? Where do they come from? Why are they important? What do they do to the galaxies that host them? And perhaps most chillingly, could they destroy us one day? We're going to peel back the layers of the universe tonight. No surface-level fluff. This is a deep dive, a cosmic unraveling. We'll explore the very edge of what we know, and everything that we fear we don't. Because UFOs from active galactic nuclei aren't just fascinating, they are foundational to the evolution of everything in the universe. To understand them, though, we must begin by standing on the edge of darkness, at the doorstep of the most misunderstood yet omnipresent monsters in the cosmos, supermassive black holes. Black holes are often portrayed as cosmic vacuum cleaners, sucking in everything in sight. That image is both useful and misleading. In truth, most black holes spend their time dormant, invisible, cloaked in silence. But in the hearts of galaxies where gas and dust are plentiful, some black holes awaken. They start feeding. And when they do, they create one of the most spectacular and terrifying phenomena in the known universe: active galactic nuclei. These nuclei are blindingly luminous. Some outshine their entire host galaxy. Picture a single point of light brighter than billions of stars combined. That's not an exaggeration. That's reality. Here's where it gets intense. As matter spirals inward toward the black hole, it forms a spinning, superheated disk, an accretion disk, and in the process, it heats up to millions of degrees. This disk emits radiation, often in X-rays and gamma rays, and also triggers powerful magnetic fields and shockwaves. But here's the kicker: not all of that matter gets swallowed. Some of it gets redirected, accelerated outward at insane speeds, by forces we still don't completely understand. And that's when ultra-fast outflows are born. These winds aren't your everyday cosmic breeze. They're accelerated to a significant fraction of the speed of light. Some reach 30% the speed of light, nearly 100,000 kilometers per second. That's fast enough to circle the Earth in less than half a second. Fast enough to escape a galaxy. Fast enough to rip stars apart, compress interstellar gas, and either trigger or halt star formation across thousands of light years. The first time scientists detected these outflows, they didn't know what to make of them. They were spotted in X-ray spectrums, absorption lines in light that didn't make sense, shifting in ways that suggested unbelievable velocity. At first, they were thought to be anomalies, glitches in data. But over time, as observations stacked up and patterns emerged, a picture began to form. These weren't flukes. They were everywhere. Quasars, Seyfert galaxies, and other AGNs all showed signs of these mysterious, ultra-fast expulsions of matter. We now believe that a majority of actively feeding supermassive black holes generate these winds at some point. And while their cause remains partially shrouded in mystery, theories abound. Some suggest the winds are launched by radiation pressure, a kind of light-powered acceleration, where intense radiation from the accretion disk literally pushes particles outward. Others believe magnetic fields play a crucial role, flinging matter away from the poles of the disk like a slingshot. Still others propose that thermal expansion, from gas heating up near the event horizon, explodes outward in a cosmic tantrum. Whatever the cause, the result is the same: shockwaves ripple through the galaxy. Interstellar gas clouds are compressed, or scattered. Star-forming regions are ignited, or extinguished. Whole stellar nurseries are silenced. In a very real way, these UFOs are cosmic regulators. They dictate how galaxies live, breathe, and die. This is called AGN feedback, a process by which the black hole influences the evolution of its host galaxy. It's one of the most crucial yet elusive components of modern astrophysics. Without it, our models of galaxy formation fall apart. We can't explain why some galaxies stop forming stars. We can't explain the relationship between galaxy mass and black hole mass. We can't explain the balance we observe in the universe. And still, we don't know how these outflows really work. There are layers to this mystery, because not all AGNs produce outflows at the same speed or intensity. Some are relatively weak. Others are unbelievably powerful. And there's even evidence that these outflows can vary over time, flickering on and off like a light switch, influenced by changes in the accretion disk or external galactic events. Even more puzzling, recent observations from telescopes like Chandra, XMM Newton, and New Star have shown that some of these outflows aren't just fast, they're structured. Like jets within jets. Some contain clumps of gas. Some contain ionized elements traveling at different speeds. There are even hints that some UFOs may evolve into larger galactic structures, radio jets, or even Fermi bubbles, bubbles of energetic plasma spanning tens of thousands of light years. Let that sink in. A single black hole, invisible and infinitely dense, can launch matter into space at nearly light speed, and that matter can reshape a galaxy and persist for millions of years. So here's the question: what happens if one of these UFOs was pointed in our direction? What would we see? Could it reach us? Could it harm us? That's not just a science fiction scenario. It's a real astrophysical possibility. But to explore that, we have to go deeper. To even begin to understand ultra-fast outflows, we have to take a journey to the hearts of galaxies, specifically, to active galactic nuclei, or AGNs. These are the most luminous, most energetic, and most violent places in the universe. An AGN is powered by a supermassive black hole, one that's millions to billions of times the mass of our Sun. But the black hole itself doesn't shine. It's the accretion disk around it, the swirling, glowing disk of matter being pulled inward, that generates the staggering light and energy we observe. As matter spirals in, it's compressed, heated, and torn apart, releasing energy in the form of radiation and high-energy particles. Magnetic fields twist and snap. Radiation pressure mounts. Somewhere in this chaotic environment, something triggers matter to be expelled, not just up, not just out, but at relativistic speeds, and in quantities that boggle the mind. Now the big question: how are these ultra-fast outflows launched? There are a few competing theories, and each one reads like the plot of a science fiction thriller. One theory involves radiation pressure. As the accretion disk emits intense radiation, this pressure acts on the surrounding gas. If the gas becomes ionized, stripped of its electrons, it interacts differently with the radiation, allowing some particles to get pushed outward rather than inward. Under the right conditions, this creates a force strong enough to eject the gas at incredible speeds. Another theory points to magnetohydrodynamic forces, an unholy alliance between magnetic fields and plasma physics. In this model, twisted magnetic field lines anchored in the accretion disk act like cosmic slingshots. As they unwind, they fling ionized matter outward with immense force. This could explain the collimated nature of many observed outflows, narrow, focused streams of energy and particles shot out like bullets from a galactic railgun. But here's where the real mystery kicks in: UFOs aren't just rare outliers. We now believe they're common, present in up to 40% of all AGNs we've studied in X-ray wavelengths. Which means that what was once considered an exotic phenomenon might actually be a fundamental process in the life cycle of galaxies. Ultra-fast outflows could be the universe's way of keeping galaxies in check. You see, if left unchecked, galaxies could theoretically grow massive beyond reason, stars forming in hyperclusters, black holes feeding forever, creating ever more chaos. But when a UFO blasts out from a central AGN, it can sweep away the surrounding gas, the very gas that forms new stars. This process, known as AGN feedback, regulates the growth of galaxies by suppressing star formation. In essence, these outflows may be the universe's method of cosmic population control. That's the poetic angle. The more terrifying one? We have no control over them, no understanding of how long they last, how frequent they are, or what exactly determines their speed and direction. Some UFOs may last for millions of years. Others could erupt and vanish like flickers of a candle in the galactic dark. Observing these outflows is no simple task either. We can't see them in visible light. They don't glow like stars or radiate like galaxies. Instead, we detect them through X-ray spectroscopy, using space telescopes like Chandra, XMM Newton, and NuSTAR. What we see are telltale absorption lines in the X-ray spectrum of the AGN, specific gaps where certain elements, like iron, have absorbed the energy. From the Doppler shift of these lines, we can infer the speed at which the gas is moving, and it's here that we find the shocking truth. The gas isn't drifting. It's tearing away from the galaxy at breakneck speed. Some AGNs show outflows moving at 10,000 kilometers per second. Others? 30,000 kilometers per second. And the fastest ever detected? 0.3 c, nearly a third of the speed of light. That's not just fast, that's insanely fast. For comparison, the fastest spacecraft ever launched by humanity, the Parker Solar Probe, travels at around 0.00067 c. That's more than 400 times slower than these outflows. And then there's the energy scale. A single ultra-fast outflow can carry energy equivalent to billions of supernovae. That's enough to heat, stir, and blast away entire clouds of interstellar matter. In the long term, this could fundamentally alter the chemical makeup, structure, and life potential of entire galaxies. And yet, the mechanism of this phenomenon still eludes us. We don't know whether it's a smooth, continuous flow, or a chaotic storm of intermittent blasts. Some data suggests that these outflows fluctuate on timescales of days, weeks, or even hours, changing velocity and density like a living, breathing thing. It's as if the galaxy has lungs, and it's exhaling plasma at light speed. Here's another wrinkle. Ultra-fast outflows might be connected to quasar winds and broad absorption line quasars. These are other high-speed outflow phenomena observed in the universe. Are they part of the same family? Are we just seeing different stages of the same cosmic weather system? Or are they completely separate processes, sharing only the spectacle of speed and power? The truth is, we're still in the infancy of understanding these objects. Every new observation raises new questions. Every new theory branches into dozens of sub-theories. And as our instruments become more advanced, with missions like Athena and XRISM on the horizon, we're poised to uncover even more jaw-dropping details. But the rabbit hole goes deeper. Some scientists have suggested that these outflows might be linked to the growth cycles of black holes themselves. That they aren't just side effects, but essential mechanisms by which black holes regulate their own feeding. By ejecting part of the infalling matter, they may be preventing overgrowth, maintaining a balance between chaos and stability. Still others have speculated on a more speculative, controversial frontier, that these outflows may hold clues about dark energy and the cosmic expansion. Could they interact with the large-scale structure of the universe? Could they be influencing the shape and behavior of the cosmic web itself? Could there be a deeper, hidden law of physics that governs when and how these eruptions occur? We don't know. But what we do know is this: if you want to understand the life cycle of galaxies, if you want to peer into the mind of the cosmos itself, then ultra-fast outflows aren't just a footnote, they are the headline. And the more we look, the more we find. Massive galaxies with dormant AGNs suddenly roaring to life. Black holes that seemed quiet suddenly erupting in million-degree winds. And all of it happening in places so far away that the light reaching us today left its source before humans had even evolved. You're watching ghosts of ancient violence. Celestial tantrums frozen in time. The ultimate act of cosmic rebellion, matter, spat out by the most powerful force in the universe. But the question still burns: are we seeing a beginning? Or an ending? One of the leading theories involves radiation pressure, the sheer force of light itself. It sounds bizarre, but light isn't just a passive glow. It carries momentum. When photons slam into particles of matter, they can transfer that momentum and push the material outward. In the extreme environment around an AGN, the radiation is so intense that it can actually blow away gas and plasma. Not in a gentle breeze, but in a storm of unimaginable fury. But there's a catch. This mechanism, called line driving, works best when the outflowing gas contains partially ionized atoms. Too little ionization and the radiation can't effectively push the gas. Too much, and there's nothing left to push against. It's like trying to push steam with your hand. So how, in this turbulent, superheated zone, does the ionization reach just the right balance to sustain an ultra-fast outflow? This is where magnetic fields enter the picture. Another theory suggests that magnetohydrodynamic, MHD, forces are at play. Picture the swirling accretion disk like a vast whirlpool of electrically charged plasma. Now imagine that embedded within that disk are magnetic field lines, twisting and warping like tangled rubber bands under tension. Under the right conditions, these lines snap, catapulting plasma away from the disk at high speeds, not unlike a solar flare but on a galactic scale. These magnetic field-driven jets could explain the immense velocities we observe, especially when the speeds approach relativistic levels, where the effects of Einstein's special relativity start to become noticeable. Matter accelerated this way could punch through the surrounding gas, leaving behind shockwaves, turbulence, and a trail of ionization like cosmic graffiti. But here's where things get even stranger. Now, imagine the implications of these outflows not just as local events, but as cosmic sculptors. Ultra-fast outflows aren't just dramatic for their speed or energy. They are galactic architects, capable of shaping the evolution of entire galaxies. How? Through something astrophysicists call feedback. Let's say you have a galaxy forming stars at a rapid pace. That's great. New stars mean new planetary systems, new chances for life. But if too many stars form too quickly, the galaxy risks burning through its fuel too fast. Enter the AGN. When a supermassive black hole becomes active, it starts flinging out these ultra-fast outflows. And those outflows slam into surrounding gas clouds, the same clouds that would otherwise condense into stars. These high-speed winds can heat, disperse, or outright blow away star-forming material. It's like a giant cosmic reset button. The AGN chokes off star formation before the galaxy exhausts itself. In this way, UFOs regulate galaxy growth, balancing the chaos of creation with the violence of destruction. It's a feedback loop so perfectly brutal that scientists believe it may explain why massive galaxies don't form infinite numbers of stars. And yet, this mechanism, one that helps dictate the life cycles of galaxies, is still poorly understood. One reason is observational. Ultra-fast outflows are incredibly difficult to detect. They don't emit much visible light. Instead, they leave their fingerprints in X-ray spectra, in the form of blue-shifted absorption lines. That means astronomers must use space-based telescopes like XMM Newton or Chandra to spot the telltale signs of gas racing toward us at tens of thousands of kilometers per second. These blue shifts indicate that the gas is moving toward us, fast. So fast, in fact, that some absorption features appear offset by significant fractions of the speed of light. These are not gentle flows. They are ripping, howling gales of ionized matter, and they only last a few thousand years, blink-of-an-eye moments on galactic timescales. What they look for are absorption lines in the spectra of X-rays emitted by the hot gas around the AGN. These lines are shifted toward the blue end of the spectrum, hence, blue shifted, which means the gas is moving toward us at incredible speeds. And these aren't minor shifts. Some of these outflows have been clocked at 0.1 to 0.3 times the speed of light, or roughly 30,000 to 90,000 kilometers per second. These are not just breezes. They're hurricanes of radiation and plasma ripping through interstellar space. What's even more fascinating is that ultra-fast outflows appear to be ubiquitous in certain types of AGNs. Studies have shown that up to 40% of bright quasars, the most luminous type of AGNs, show evidence of UFOs in their X-ray spectra. This suggests that these phenomena aren't just oddities or cosmic accidents. They're likely a core component of how galaxies evolve. Yet, despite their prevalence, they remain deeply mysterious. Their structure, origin, mass, and energy content are all subjects of ongoing research and debate. There's also a strange duality to them. On one hand, they are destructive, capable of tearing apart star-forming regions and halting galactic growth. On the other, they are necessary. Without these feedback mechanisms, many galaxies would grow too large, too fast, and become unstable. The very existence of well-formed spiral galaxies like the Milky Way may depend on this violent regulation system. It's a cosmic irony. Galactic life is shaped and sustained by forces of unimaginable violence. Now let's zoom in. Imagine a black hole with a mass of 1 billion suns, quietly spinning at the center of a galaxy 1 billion light-years away. Around it, an accretion disk glows like a miniature sun, made of matter falling inexorably inward. Closer to the black hole, gravity begins to twist space and time. Gas near the event horizon moves at relativistic speeds, heated to millions of degrees, glowing in X-rays. Somewhere in this hellish cauldron, conditions align perfectly, and a surge of radiation or magnetic tension launches a torrent of plasma into space. That's your UFO. That's the beast we're talking about. These outflows don't just shoot off randomly. They often have preferred directions, usually perpendicular to the plane of the accretion disk. In some AGNs, they are tightly collimated, forming narrow jets. In others, they expand in wide-angle flows, affecting large volumes of interstellar medium. The geometry of these outflows is one of the biggest unknowns in modern astrophysics. Are we only seeing them when we happen to look down the barrel of a jet? Or are they more widespread, hidden in angles we haven't observed yet? Another mind-bending aspect is the mass loss rates associated with UFOs. Some estimates suggest that AGNs can expel up to several solar masses of material every year through these outflows. That might not sound like much until you remember that this is being done by an object smaller than the solar system. This is like a pinhead ejecting the mass of an entire star every year. It's an astonishingly efficient and violent process, one that challenges our understanding of black hole physics and energy transfer. And if you're thinking all of this happens quietly in deep space, think again. These outflows generate shocks as they slam into surrounding matter. Those shocks heat the gas to millions of degrees, producing emissions across the electromagnetic spectrum, from X-rays to radio waves. In some galaxies, astronomers have detected these shock fronts spreading outward like ripples in a pond, except the pond is 100,000 light-years across, and the ripple is moving at a significant fraction of light speed. It's the kind of visual that reminds us just how small we really are. What's even more mysterious is how ultra-fast outflows interact with their host galaxies over cosmic timescales. Do they trigger new waves of star formation by compressing gas in certain regions? Do they permanently sterilize parts of the galaxy, turning fertile clouds into barren voids? The answer might be both. In fact, some models suggest a two-phase feedback process. First, a positive phase where gas is compressed and stars are born, followed by a negative phase where the remaining gas is blasted away, halting star formation. Interestingly, UFOs might also be connected to another astrophysical enigma, broad absorption line, BL, quasars. These are quasars with wide, deep absorption features in their ultraviolet spectra, believed to be caused by high-velocity winds. while balls are typically slower than UFOs, more like 0.01 to 0.1 times the speed of light. Their underlying mechanism may be similar, with UFOs representing an even more extreme version. Some scientists propose that balls and UFOs are simply different manifestations of the same fundamental process, seen at different angles or energy levels. And speaking of angles, our perspective matters a lot. The detection and characteristics of UFOs depend heavily on how we're viewing the AGN. A slight tilt in the orientation of the accretion disk can obscure or reveal different spectral features. That means our current understanding is based on a sample bias by our vantage point. We're piecing together a 3D puzzle using 2D snapshots from millions of light years away, like trying to understand a hurricane from a single satellite image. The more we study these ultra-fast outflows, the more we realize they don't just teach us about black holes. They offer insights into the fate of the universe itself. Galaxies are the building blocks of the cosmos, and AGNs sit at their cores like engine rooms. The behavior of UFOs helps determine how galaxies live, evolve, and die. They affect the distribution of matter, the growth of cosmic structures, and possibly even the conditions for life in the universe. And here's where things get really weird. Some scientists are beginning to explore whether ultra-fast outflows could be tied to cosmic entropy and the heat death of the universe. If AGNs continue to spew energy and matter over billions of years, they could accelerate the process of cosmic homogenization, the gradual flattening of all temperature and energy differences in the universe. In this way, UFOs might not just be galactic weather patterns. They could be the carriers of entropy, whispering the slow and inevitable end of all things. And yet those very forces are what keep galaxies from tearing themselves apart in unbridled growth. The universe, it seems, is not built on balance through peace, but through carefully managed chaos. Ultra-fast outflows are the universe's version of controlled demolition, knocking down what would otherwise overgrow, so that structure and harmony can emerge from a dance of destruction. Another element that makes ultra-fast outflows so compelling is how deeply they connect the smallest and largest scales of the universe. Think about it. These outflows originate from regions no larger than our solar system, right around the black hole. And yet they influence the fate of galaxies that span hundreds of thousands of light years. How can something so tiny exert control over something so vast? The answer lies in the raw power of the black hole and the mechanisms it uses to convert gravitational energy into kinetic fury. Let's not forget, when matter falls into a black hole, it doesn't just vanish. Before crossing the event horizon, that matter is violently accelerated, crushed, and heated to millions of degrees. The friction, magnetic tension, and radiation pressure involved in this final death spiral are so extreme that more energy can be released in this process than in a supernova explosion. That energy must go somewhere, and often, it is redirected outward, sometimes vertically from the accretion disk, blasting into the surrounding medium. These are the outflows we see, signals of a death that fuels rebirth on a galactic scale. What complicates this picture even further is that these outflows don't always travel in straight lines. Unlike jets, which are highly collimated streams of particles often seen shooting directly outward from a black hole's poles, ultra-fast outflows are more chaotic. They expand in wide angles. They don't maintain strict paths. They slam into clouds, twist to warped magnetic fields, and sometimes even interact with other layers of galactic gas. This gives rise to turbulence, compression fronts, and shockwaves that ripple across thousands of light years. When these shockwaves hit dense clouds of gas, the result can go either way. In some cases, the gas is dispersed and star formation is quenched. In other cases, the compression actually triggers star formation, as the shockwave forces clouds to collapse under their own gravity. This dual nature adds another layer of mystery. Are ultra-fast outflows primarily destructive, or do they also play a role in creating the very stars they are supposed to stop? The answer is both. The universe is not binary. It's a complex tapestry where destruction and creation often occur in tandem. Then there's the question of timescales. Ultra-fast outflows are fast, but they're not brief. These events can last for millions of years, gradually altering the structure of their host galaxies. Over cosmic time, The cumulative effect of multiple outflow episodes can transform a galaxy's shape, color, and composition. A once blue, star-forming galaxy might turn red and quiescent, its gas reservoirs blown away or locked into new stars. That means these phenomena are key actors in the cosmic life cycle, deciding whether a galaxy continues to flourish or drifts into old age. Interestingly, these outflows may also solve another cosmic riddle: why are some galaxies dormant? Astronomers have long puzzled over why many large galaxies appear to have stopped forming stars billions of years ago. One leading hypothesis is that AGNs, and specifically their ultra-fast outflows, are responsible. By expelling the gas needed for star formation, or by heating it so that it can no longer condense, UFOs may have put these galaxies into long-term hibernation. The engines of creation were not broken, they were shut off by design. The mass and energy involved in these outflows are also staggering. Some UFOs carry as much mass per year as hundreds of Earths, and their kinetic energy is often comparable to the total radiative output of the AGN itself. That means these are not side effects or noise in the system, they are major, perhaps even dominant, aspects of the AGN's influence. We're talking about phenomena that can pump 10 to the power of 45 ergs per second into their surroundings. That's more energy every second than the sun emits in over 1,000,000 years. So where does all this mass go? Some of it slams into nearby clouds. Some of it escapes into intergalactic space. And some of it falls back down into the galaxy's disk, cooled and slowed, forming galactic fountains that may recycle material back into future stars. The cycle isn't linear, it loops, recycles, and adapts. The gas ejected in one era might be the cradle of stars in the next. It's an elegant yet violent balance, with ultra-fast outflows as both destroyers and midwives of cosmic evolution. As our observational technologies improve, we're beginning to get more granular with these outflows. Using instruments like the New Star Telescope, Athena, and the upcoming XRISM mission, astronomers can resolve finer features in X-ray spectra than ever before. This allows them to map not just the speed, but the structure, temperature, and chemical composition of the outflowing gas. What we're finding is both expected and baffling. Heavy elements like iron and silicon are being carried away at near-light speeds, spreading the seeds of future solar systems across intergalactic distances. This brings us to one of the most profound realizations. We may owe our very existence to these outflows. The iron in your blood, the calcium in your bones, the oxygen you breathe, these elements were forged in stars and spread across space through violent events. Supernovae were part of that story, but so were these outflows. Without them, galaxies wouldn't redistribute their elements efficiently. The building blocks of life might remain trapped in the core, never reaching the outskirts where stars and planets can form. Ultra-fast outflows are not just violent, they are life-generating on a universal scale. And as if all of this wasn't enough, there's growing evidence that these outflows may interact not just with matter, but with dark matter itself. While dark matter does not emit, absorb, or reflect light, it does have gravitational effects. Some simulations suggest that the powerful feedback from AGN outflows can stir or redistribute dark matter halos surrounding galaxies. That opens up a whole new avenue of questions. Could UFOs be indirectly shaping the invisible scaffolding of the universe? Are they not only regulators of baryonic matter but also sculptors of the cosmic web? They are less like a focused laser beam and more like a cosmic firestorm, erupting in multiple directions, interacting with the surrounding gas, and creating a kind of turbulent shell around the AGN. This chaotic geometry makes them harder to model and predict, but also far more interesting. Instead of narrowly affecting a small portion of their host galaxy, UFOs can impact vast swaths of interstellar medium, potentially disrupting star formation across large regions. And speaking of star formation, here's where things get even stranger. Some researchers suggest that ultra-fast outflows might not only quench star formation, but trigger it in certain environments. How could that be? When a fast-moving outflow slams into a dense gas cloud, it can compress the gas, raising the local pressure and causing the cloud to collapse, a key ingredient for forming new stars. So, while these outflows often act as galactic breaks, in some contexts, they might serve as catalysts for creation, forcing matter to condense and ignite into newborn suns. This dual role, destroyer and creator, adds layers of complexity to our understanding of AGNs. It also raises questions about the broader role of black holes in the universe. Are they just mindless consumers, devouring matter without purpose? Or are they, paradoxically, also cosmic regulators, gatekeepers of galactic evolution? The data suggests the latter. In fact, modern simulations of galaxy formation can't match real-world observations unless AGN feedback is included. Without UFOs and similar phenomena, galaxies grow too massive, too fast, and too luminous, defying what we actually see in space. Now let's zoom back in. The detection of UFOs relies on subtle signals, minuscule dips in X-ray spectra that require highly sensitive instruments and painstaking analysis. And these dips aren't random, they correspond to specific elements, like iron, silicon, and oxygen, that absorb X-rays at known energies. By measuring how much these lines are shifted and how deep they are, astronomers can estimate not only the velocity of the outflow but also its density, temperature, and ionization state. From that, they can infer how much mass is being carried away, and how much kinetic energy the outflow is injecting into the galaxy. And the numbers are staggering. Some ultra-fast outflows carry enough kinetic energy to rival the luminosity of the entire galaxy itself. In other words, a single black hole, through its chaotic feeding process, can generate winds that outshine billions of stars combined. That's not just wild, it's a hint that black holes, once thought to be silent and passive, are among the most influential engines in the cosmos. But what truly adds a layer of intrigue is how UFOs could be tied to the earliest epochs of cosmic history. We've detected AGNs and quasars from when the universe was less than 1 billion years old, meaning these ultra-fast outflows have been shaping the cosmos almost from the beginning. They may have influenced how the first galaxies assembled, how the first stars formed, and even how elements were distributed across intergalactic space. In fact, some theorists believe UFOs might be responsible for spreading metals, elements heavier than helium, into vast regions of the early universe, seeding future generations of stars and planets. Still, questions abound. What causes some AGNs to produce ultra-fast outflows while others remain quiet? Is it related to the black hole's mass? Its spin? The orientation of the accretion disk? Or could it be a phase, an episodic event that comes and goes as the black hole evolves? Some AGNs show evidence of UFOs one year, and then silence the next, hinting at a highly dynamic and variable process. Then there's the mystery of structure. Are these outflows smooth, continuous winds? Or are they clumpy, filled with dense blobs of gas moving at different speeds? Some observations suggest the latter, indicating that these outflows might contain substructures, shock fronts, eddies, and density waves that ripple through space like the surface of a stormy sea. If that's true, then modeling them becomes even more difficult, requiring high-resolution simulations that can handle the complex physics of turbulence, radiation transfer, and magnetic instability all at once. Theoretical astrophysicists have started creating 3D simulations of ultra-fast outflows, trying to replicate what's observed in X-ray data. These simulations, run on supercomputers, incorporate thousands of equations describing everything from fluid dynamics to general relativity. What they've discovered is jaw-dropping. Under the right conditions, an AGN can inject enough energy into its host galaxy to completely shut down star formation within a few million years, a blink of an eye in cosmic time. But even that is just the surface. Because once these outflows move beyond their host galaxy, they may keep going, punching into the circumgalactic medium, the vast halo of gas that surrounds galaxies, and even beyond that into the intergalactic medium, the diffuse gas that threads between galaxies like an invisible web. This raises a profound idea. Ultra-fast outflows might be part of a cosmic circulation system, ferrying material across vast distances and connecting galaxies in subtle but meaningful ways. And if that's the case, then UFOs aren't just localized events. They're part of a grand, interwoven process of cosmic ecology. Like winds that move across continents on Earth, distributing heat, moisture, and life, these galactic winds might be spreading metals, regulating star birth, and shaping the evolution of cosmic structures on the largest imaginable scales. On the heart of these phenomena, the central engine of the active galactic nucleus. At its core lies a supermassive black hole, often millions or even billions of times the mass of our Sun. But the black hole itself isn't what shines. It's the accretion disk swirling around it, an inferno of gas and dust spiraling inward at relativistic speeds, that emits the intense radiation. And it's from this very disk that the ultra-fast outflows are thought to be launched. The exact mechanism remains one of the deepest mysteries in astrophysics. Some theories suggest that radiation pressure from the intense light emitted by the accretion disk is enough to blow material away at high speeds. Others point to magnetohydrodynamic forces, where magnetic fields twisted and wound up by the spinning disk create powerful winds that fling material outward. And then there are models that involve thermal pressure, where the superheated gas builds up enough energy to break free. Most likely, it's a combination of all three, a perfect storm of radiation, magnetism, and heat all working together to fuel these extraordinary winds. But there's a deeper mystery. Some ultra-fast outflows seem too powerful, more energetic than the radiation from the disk alone could account for. This hints at another layer of complexity. Could the black hole's spin play a role? A rapidly spinning black hole might drag spacetime around with it, a process known as frame dragging, and potentially launch even more energetic outflows through mechanisms like the Blandford-Zajic process, which extracts energy from the black hole's rotation itself. If this is the case, then UFOs aren't just byproducts of accretion. They might be tapping directly into the rotational energy of the black hole, making them even more exotic than we imagined. Observationally, measuring these outflows is an art in itself. Scientists must capture X-ray light from extremely distant galaxies and parse subtle features buried in noise. The instruments used, like Chandra, XMM Newton, and more recently, NuSTAR, must be precisely calibrated to detect these blue-shifted absorption lines. Each detection represents an outflow that was launched millions or even billions of years ago, and the light is only just now reaching us. This means that every time we observe a UFO, we are looking deep into the past, catching a galaxy in the middle of a pivotal, violent transformation. And then there's the matter of scale. The energy in some ultra-fast outflows is so massive, it rivals or even exceeds that of a supernova, the explosion of a dying star. But unlike a supernova, which happens once and is done, a UFO can last for millions of years, continuously dumping energy into its host galaxy. Some studies estimate that these outflows can carry away as much as 1,000 solar masses of material per year, disrupting the galaxy on an epic scale. These aren't just winds, they're cosmic tsunamis, sweeping across interstellar space with devastating force. As we study more galaxies, patterns begin to emerge. It seems that UFOs are most common in quasars, the most luminous types of AGNs, often seen at great distances. This makes sense, as quasars are powered by black holes that are devouring matter at ferocious rates. The more matter falls in, the more energy is available to launch these winds. But that raises an interesting point. Are ultra-fast outflows a temporary phase? Do they only occur during brief, turbulent periods in a galaxy's life, moments of intense feeding and growth, before fading away into quiescence? If so, then UFOs might be signposts of transformation, indicating a galaxy in transition. One theory is that galaxies go through quasar phases during major mergers or bursts of accretion, during which UFOs are launched, star formation is choked off, and the galaxy evolves from a blue, star-forming spiral to a red, quiescent elliptical. In this framework, UFOs are part of a cosmic life cycle, marking the moment when a galaxy grows up and leaves its wild youth behind. Yet, despite everything we've uncovered, major questions remain. How exactly are these winds collimated? Why do some AGNs have them while others don't? Are there relativistic jets and UFOs working together, or do they occur independently? And what about their impact on galactic halos, the diffuse gas that surrounds galaxies for hundreds of thousands of light years? If UFOs can reach and heat these halos, they might influence the entire ecosystem of a galaxy, preventing fresh gas from falling in and fueling new generations of stars. As astronomers continue to study these phenomena, they are turning to ever more powerful tools. The upcoming Athena X-ray Observatory, set to launch in the next decade, promises to revolutionize our understanding of UFOs. With its high-resolution spectrometers and large collecting area, Athena will be able to track the dynamics of these winds in unprecedented detail, providing 3D maps of outflows, their composition, and their impact on galactic structure. And further down the road, missions like Lynx and XRISM could push the boundaries even more. Yet even with all these advancements, UFOs remain one of the most tantalizing mysteries in modern astrophysics. They embody a paradox. Born in the smallest regions of the universe, they command influence across the largest scales. They are invisible to the human eye, yet reshape galaxies. They are transient, chaotic, and often misunderstood, but they may hold the key to understanding how the cosmos grew from a sea of gas to a tapestry of galaxies. And if there's one truth the universe keeps whispering, it's this: the more we learn, the more we realize how little we truly understand. That's mind-blowing. It means that by studying ultra-fast outflows, we're not just learning about the environment around a black hole, we're peering into the deep mechanics of the black hole itself, into the engine room of some of the most extreme objects in the universe. Now, imagine the scale of influence here. A black hole just a few light hours across is spewing winds that can affect regions tens of thousands of light years wide. It's like a pebble in a pond creating ripples that span an ocean. And those ripples, those ultra-fast outflows, don't just stir up the surrounding gas. They reshape the entire evolutionary trajectory of galaxies. In some systems, these outflows have been observed carrying more energy than all the stars in the host galaxy combined. Just sit with that for a second. One tiny central object outshining billions of stars through its violent expulsions of gas and energy. The more we observe, the more bizarre these systems become. Using observatories like XMM Newton, Chandra, and NuSTAR, astronomers have been able to track these outflows over time. And what's surprising is how quickly they can change. In some AGNs, the UFOs vary in velocity, ionization state, and mass flow on timescales of days or even hours. That tells us that these are not slow, stately cosmic breezes. They're volatile, dynamic, and reactive. They're shaped by complex feedback loops, where the black hole's feeding rate, the disk structure, and the surrounding environment are in constant interplay. Let's take a detour here and consider the observational challenges. Detecting UFOs isn't simple. These outflows reveal themselves as highly ionized, blue-shifted absorption lines in the X-ray spectrum. But these signals are faint, buried in noise, and often require weeks of observation time to pull from the data. The absorption features also overlap with other components: warm absorbers, intervening clouds, and even stellar contributions, so separating the UFO signatures is like trying to hear a whisper in a thunderstorm. It takes persistence, sophisticated modeling, and cutting-edge instruments to isolate the truth. Then there's the question of mass and momentum flux. How much material is being ejected, and with what force? This is crucial, because it tells us how much influence these outflows really have. If they're lightweight but fast, they may not carry much mass. But if they're dense and fast, their ability to carve out galactic cavities and quench star formation is immense. And recent observations suggest the latter may be true in many cases. Some UFOs seem to carry several solar masses of material per year, enough to starve a galaxy of the fuel it needs to build new stars. We've also started to see the aftereffects of ultra-fast outflows. Using radio telescopes and optical observatories, astronomers have spotted cavities and bubbles in the interstellar medium, regions where the outflows have literally blown away the gas. In some cases, there's evidence of shockwaves, like cosmic tsunamis moving through space, lighting up matter as they pass. These signatures confirm that UFOs are not just theoretical constructs. They're actively reshaping the architecture of galaxies in real time. But this only scratches the surface. The implications of UFOs reach even deeper into cosmic history. When we look at galaxies billions of light years away, we're seeing them as they were billions of years ago. And guess what? UFOs are still there, still active, still shaping the galaxies of the early universe. That means these outflows may have played a key role in setting the stage for everything we see today, including our own Milky Way. Without them, the cosmic web could have evolved into a very different structure, perhaps one where galaxies merged faster, burned brighter, and died younger. So far, we've discussed ultra-fast outflows primarily as X-ray phenomena. But there's growing evidence that they may connect to other types of AGN winds, broad absorption lines in UV spectra, radio jets, and molecular outflows seen in infrared and millimeter waves. If this is true, then UFOs aren't just one category of feedback. They're part of a multi-phase, multi-scale ecosystem of galactic regulation. They may begin as hot, ionized winds near the black hole and evolve into cooler, denser outflows that spread throughout the galaxy, interacting with gas clouds, star clusters, and even dark matter halos. And let's not overlook the exotic possibilities. Some astrophysicists have proposed that UFOs might carry clues to new physics. Could they accelerate particles to energies beyond what our particle colliders can achieve? Could they harbor signatures of quantum gravity, or offer indirect evidence of dark matter interactions in galactic cores? These are speculative questions, but they're being asked seriously by researchers who see in UFOs not just a local phenomenon, but a gateway to the deep structure of reality. Ultra-fast outflows are not just fast, they're a fast track to the most fundamental questions in cosmology. They force us to rethink what black holes do, what galaxies need, and how the universe balances the opposing forces of chaos and order. And as telescopes become more powerful, especially with the launch of next-gen observatories like Athena, Lynx, and the James Webb Space Telescope, we're poised to uncover even more secrets hiding in these high-velocity winds. This volatility also suggests that ultra-fast outflows are far from stable phenomena. Instead, they're likely episodic, bursting forth in powerful surges when conditions are right, and then fading or shifting as the black hole's feeding patterns change. It's not a gentle breeze but a series of galactic hurricanes, fueled by matter devoured and then expelled in a violent cosmic cycle. And because these changes can happen on such short timescales, catching them in the act requires both luck and incredibly precise timing with sensitive instruments. The ionization state of the outflowing gas adds another layer of strangeness. These winds are composed of highly ionized material, gas so energized by the AGN's intense radiation that electrons have been stripped from their atoms, sometimes multiple times over. We're talking about ions of iron, oxygen, neon, and other heavy elements traveling at tens of thousands of kilometers per second. This extreme ionization gives us clues about the environment around the AGN, the temperature, density, and energy levels of the wind. And by analyzing the absorption lines these ions leave in the X-ray spectra of AGNs, we can map the structure and composition of these outflows with stunning detail. But these aren't just data points. They're cosmic breadcrumbs, trails leading us to greater truths about how the universe works. For instance, when we see these outflows appearing in quasars, some of the most luminous AGNs, we begin to understand that UFOs are not rare. In fact, they may be a nearly universal feature of supermassive black hole activity, present in a significant percentage of all AGNs across the cosmos. This prevalence hints that ultra-fast outflows could play a standardized role in galactic evolution, not an occasional or incidental one. Another fascinating discovery is the relationship between the UFO's power and the black hole's Eddington ratio, a measure of how fast the black hole is accreting compared to the maximum allowed by the balance of radiation pressure and gravity. The higher this ratio, the more luminous and turbulent the accretion process becomes, and often, the stronger and faster the outflows. This correlation strengthens the theory that UFOs are fundamentally connected to the black hole's feeding frenzy. When a black hole gorges itself, it blows harder. However, there's still debate about how far these winds actually travel. Do they stall out within a few parsecs of the core? Or can they continue all the way to the galactic outskirts, sculpting entire halos of gas? Some simulations suggest that even if the winds begin at near light speeds, they may lose energy rapidly through collisions and mixing with surrounding gas, forming massive shockwaves. These interactions could heat the galactic medium, preventing gas from cooling and condensing into stars, a process known as maintenance mode feedback. Even more intriguing is the idea that UFOs might contribute to the mysterious phenomena we observe in galaxy clusters. In some clusters, astronomers have detected enormous cavities in the hot X-ray emitting gas, voids where something, long ago, pushed the plasma aside. Could ultra-fast outflows be responsible for some of these structures? It's possible. The combined effect of millions of years of AGN activity could have driven winds powerful enough to carve out these vast spaces in the intracluster medium, helping to regulate the temperature of galaxy clusters and stave off runaway star formation. We also can't ignore the implications for cosmic chemical enrichment. As these outflows tear through the interstellar medium, they carry with them enriched material: iron, carbon, oxygen, silicon, elements forged in earlier generations of stars. When these materials are expelled into the surrounding galaxy or even beyond into intergalactic space, they seed the cosmos with the building blocks of future stars, planets, and possibly life itself. So, in a sense, ultra-fast outflows are recyclers of the universe, distributing matter that once lived in stars across cosmic distances. There's even a speculative connection between UFOs and supermassive black hole growth regulation. In theory, these outflows might serve as a self-limiting mechanism. As the black hole accretes more and more material, the resulting outflows grow stronger, eventually pushing back against the inflow of gas. This feedback loop may create a natural cap on how massive a black hole can become, preventing them from growing unchecked and explaining why the largest black holes seem to plateau around a few tens of billions of solar masses. And here's where things get truly exciting. New instruments on the horizon, like the Athena X-ray Observatory and the Lynx mission, are poised to revolutionize our understanding of these outflows. With far greater sensitivity and resolution, they'll allow us to observe these winds in exquisite detail, not just their speeds and ionization, but their 3D structures, variability patterns, and interactions with surrounding matter. For the first time, we'll be able to watch ultra-fast outflows evolve in real time, like watching storms unfold on a galactic scale. This will also let us answer one of the most fundamental questions in astrophysics: how do galaxies and black holes co-evolve? It's now clear they don't grow in isolation. The growth of one influences the other. And ultra-fast outflows are likely the mechanism that makes this cosmic handshake possible. They are the conduit between a black hole's hunger and a galaxy's fate, regulating the balance of power in the most literal way. Be one of the key ingredients in galaxy formation itself. Not a rare exception, but a fundamental mechanism, like gravity or dark matter, that helps sculpt the large-scale structure of the universe. If UFOs are present in most, if not all, actively accreting supermassive black holes, then they're not just phenomena to observe, they're forces to model, to simulate, and to understand as deeply as possible if we hope to comprehend the grand narrative of cosmic evolution. Interestingly, UFOs could also help solve one of astronomy's most nagging mysteries: the discrepancy between simulated galaxies and real ones. For decades, simulations without AGN feedback, particularly without ultra-fast outflows, produced galaxies that were far too massive, too bright, and too active compared to what we see in the universe. Once researchers began to include AGN winds like UFOs in the models, things started to fall into place. Star formation dropped to more realistic levels, galaxies stopped growing out of control, and the simulated universe started to resemble our own. This means that without these furious galactic winds, the universe as we know it wouldn't exist in the same form. And yet, even with their importance acknowledged, the origin points of these outflows remain enigmatic. Exactly where within the AGN are they launched from? Some models suggest the inner edge of the accretion disk, mere light hours from the event horizon. Others propose that magnetically driven winds could form in a broader range of disk radii. Understanding the origin point is critical, not just for mapping their structure but also for understanding how they carry momentum and energy outwards so effectively across scales of tens of thousands of light years. Moreover, there's still debate over the mass loss rates of these outflows. If they are as massive as some data suggest, then UFOs could be removing more material from the galaxy than is being converted into stars, dramatically altering the life cycle of galaxies. And here's a jaw-dropping thought. If these outflows carry away enough gas, they might starve the black hole itself, cutting off its food supply and causing the AGN to flicker out temporarily or even permanently. That's cosmic irony, an object so violent that it ends up silencing itself. On the flip side, when these outflows interact with the galaxy's gas and dust, they don't just push, it's a dynamic interaction, filled with shocks, compression zones, turbulence, and localized heating. These shock fronts are like galactic weather systems, capable of igniting or extinguishing star formation depending on where and how they hit. In some galaxies, UFOs might carve out enormous bubbles or cavities, which have been observed in X-rays and radio wavelengths. These bubbles are essentially scars, visible evidence of battles between gravity and feedback, between growth and regulation. Now consider this. We've barely scratched the surface of how UFOs might influence supermassive black hole mergers. When two galaxies collide and their black holes begin to spiral toward each other, the presence of outflows could dramatically affect how much gas is available to fuel that merger. It could delay the process or change the spin orientation of the resulting black hole. UFOs, in this context, might not just regulate star formation. They might shape the timing and nature of gravitational wave events produced by black hole collisions. Let's not forget about the connection between UFOs and cosmic chemical enrichment. These winds carry not just gas, but also heavy elements forged in the cores of stars and released through supernovae. When UFOs sweep through a galaxy, they spread these elements across vast regions, seeding the intergalactic medium with the building blocks for future planets, moons, and even life. Without mechanisms like these, the universe would remain chemically barren, rich in hydrogen and helium, but poor in carbon, oxygen, iron, and everything else that makes complex structures, including us, possible. The very detection of UFOs is a marvel of technology. Since these winds are composed of ionized gas traveling at tens of thousands of kilometers per second, they can only be observed in specific high-energy bands, primarily in the X-ray part of the spectrum. That's why telescopes like Chandra, XM Newton, and now's RISM are so crucial. They allow scientists to detect the telltale blue shifted absorption lines that indicate material moving toward us at insane velocities. In some AGNs, these lines are shifted by up to 10% of the speed of light, a stunning measurement by any standard. These observations require not just raw power but also finesse. High-resolution spectrometry, long exposure times, and the ability to differentiate between layers of gas at different ionization states and velocities are essential. And even then, interpretation is difficult. The data is often noisy, with overlapping signals and varying levels of uncertainty. Astronomers must use complex computer models to simulate what kind of outflow geometry, density, and ionization would produce the observed spectrum. And yet, despite these challenges, the signals are clear enough to paint a picture of an incredibly violent and dynamic environment. The diversity among observed UFOs is also striking. In some AGNs, the outflows are relatively narrow and consistent. In others, they're multi-phase, with several distinct components moving at different velocities and carrying different types of ions. This variability suggests that each AGN is unique, shaped by the specific conditions around its black hole, the accretion rate, magnetic field configuration, orientation, and the history of past activity. There is no one-size-fits-all model, which makes the study of UFOs a continuously evolving and deeply creative field. Another mystery is how these UFOs relate to other types of AGN winds, like broad absorption line (BL) winds or warm absorbers. Are they part of the same phenomenon, viewed from different angles? Or are they fundamentally different processes, with unique origins and effects? Some theories suggest a kind of wind stratification, where ultra-fast outflows represent the innermost, hottest, and most energetic layer, surrounded by slower, cooler winds farther out. If this model is accurate, then UFOs might be the inner engine of a much larger feedback mechanism, a hidden core of fire inside the galactic storm. And what about the future? As we build more powerful observatories, like the Athena X-ray Observatory, slated for the 2030s, we'll gain even sharper eyes on these mysterious outflows. With better resolution, we might detect even faster winds, or trace how the outflows evolve over weeks, months, or even decades. We might begin to answer questions we can barely phrase today. How common are relativistic UFOs? Do their characteristics correlate with black hole spin? Can they serve as precursors or predictors of AGN shutdowns or reignitions? How much mass and energy these ultra-fast outflows are truly transporting? Are we talking about a few solar masses per year being ejected from the black hole's vicinity? Or something far more substantial, hundreds of solar masses annually, enough to clear out the entire central region of a galaxy? The uncertainty comes from the difficulty in measuring both the density and volume of the outflowing gas. Even a small variation in one of these parameters can lead to vastly different estimates of the total impact. This is why astronomers often speak in terms of ranges or probabilities when modeling UFOs. We're still working with incomplete information about a profoundly complex system. One of the most fascinating consequences of these outflows is their ability to compress gas in certain regions, triggering a paradoxical effect. Rather than halting star formation, they may sometimes initiate it. If a UFO slams into a dense pocket of interstellar medium, the shock wave can compress the gas, creating the high-pressure conditions necessary for new stars to form. So in some galaxies, ultra-fast outflows might act like both the destroyer and the creator, a kind of cosmic yin and yang. Whether they quench or ignite star formation may depend on their speed, direction, energy, and the structure of the gas they encounter. There are even broader implications. Because UFOs are detectable at great distances, they serve as powerful tools for probing the early universe. Some quasars we see today are so distant that their light has traveled for more than 12 billion years, showing us what galaxies looked like when the universe was just a few 100 million years old. And remarkably, UFOs have been detected in these early quasars, suggesting that black holes were already shaping galaxy growth from the very beginning. The fact that UFOs existed so early in cosmic history raises questions about how quickly black holes grow and how soon they begin influencing their surroundings. How did supermassive black holes in the early universe acquire such mass in such short times? Some theories point to direct collapse black holes, primordial giants that skipped the usual supernova stage and formed from massive gas clouds. Others suggest rapid, uninterrupted feeding in chaotic environments. Whatever the case, the presence of ultra-fast outflows in young galaxies tells us that black hole feedback was already in full swing, sculpting and regulating galaxies just as they were beginning to form. What makes this even more astonishing is that ultra-fast outflows aren't just limited to theoretical models or exotic AGNs. They're turning up in observational data from a wide variety of systems, from luminous quasars to low-luminosity AGNs in nearby galaxies. This indicates a continuum of outflow strength and behavior, meaning that even relatively quiet black holes might occasionally belch out ultra-fast winds if the conditions are right. It's like finding out that not only volcanoes erupt, but so do small hills, given the right internal pressure. Then there's the role of magnetic fields, a wild card in many models but potentially the linchpin in explaining UFOs. Theories involving magnetohydrodynamic, MHD, winds suggest that twisted magnetic fields anchored in the accretion disk could fling matter outward at incredible speeds, almost like cosmic slingshots. These magnetic fields could extract rotational energy from both the disk and the spinning black hole itself, driving massive outflows with remarkable efficiency. In this picture, the black hole is not just passively consuming, it's also powering colossal winds through the electromagnetic tension of spacetime itself. To test these ideas, astronomers rely on cutting-edge observations in X-ray wavelengths, where the signatures of UFOs are most visible. Absorption lines caused by highly ionized iron, like Fe-XXV and Fe-XXVI, are key indicators. These lines shift toward higher energies if the gas is moving toward us at high speeds, allowing astronomers to calculate velocities and ionization parameters. High-resolution X-ray spectrometers, like those aboard ESA's XMM Newton or NASA's Chandra X-ray Observatory, have made it possible to detect these signatures with unprecedented precision. And yet, limitations persist. The data we have is often noisy, sparse, or only covers a brief moment in time. That's why future observatories like Athena, Advanced Telescope for High-Energy Astrophysics, are eagerly anticipated. With vastly improved resolution and sensitivity, Athena will allow astronomers to monitor AGNs and their outflows continuously, revealing not only the structure of UFOs but also their evolution. We'll be able to witness changes in real time, like tracking the course of a storm across an alien world. This real-time monitoring is crucial. If UFOs vary on hourly or daily timescales, then long-term observation campaigns could reveal cyclical behavior, patterns of acceleration and deceleration, or even evidence of magnetic reconnection events within the accretion disk. It would be like watching the beating heart of a galaxy, one pulse of energy after another, radiating outward through space and time. And with enough data, we might finally crack the code of how these outflows originate, evolve, and influence everything around them. Moreover, ultra-fast outflows may help solve the puzzle of galactic alignment. Observations have shown that some galaxies, particularly those with AGNs, exhibit a peculiar alignment between the rotation axis of their central black hole and the large-scale structure of the surrounding cosmic web. Could the outflows from AGNs be playing a role in this alignment? Could the direction of UFOs actually shape the orientation of the galaxy's disk or influence the infall of future material? If so, then these high-speed winds aren't just regulating mass. They're orchestrating cosmic choreography on an intergalactic scale. And what if we could recreate conditions similar to ultra-fast outflows here on Earth? Particle physicists have drawn parallels between UFOs and plasma jets observed in laboratory fusion experiments. Understanding how energy and matter flow in AGNs could inform nuclear fusion technology, or vice versa. The physics of turbulent plasmas, magnetic reconnection, and high-velocity ionization is universal. The more we study UFOs in the sky, the better we might understand energy systems in our own world. Black holes were already exhibiting this aggressive, galaxy-shaping behavior soon after the Big Bang. This discovery has profound implications. It tells us that ultra-fast outflows didn't emerge late in cosmic history as a byproduct of galactic maturity. They were there from the beginning, woven into the fabric of cosmic evolution from its earliest epochs. These newborn black holes weren't quietly growing in isolation. They were howling with energy, launching winds that altered their surroundings from the very start. And the question becomes, how did black holes in such a young universe become massive enough, fast enough, to generate these violent outflows? Theories range from the rapid collapse of massive primordial gas clouds to the merging of dense stellar remnants, but no answer is fully satisfying yet. What is clear, though, is that UFOs aren't a marginal detail. They are signposts of violent transformation, stamped across the observable universe like scars left by a raging storm. Another aspect that makes ultra-fast outflows so compelling is their multi-phase structure. These aren't uniform winds made of a single type of gas moving at a single velocity. Instead, they are turbulent systems with layers of different temperatures, ionization states, and velocities. Some portions of the wind are hotter and more diffuse, while others are cooler and denser. This complexity makes them incredibly difficult to model, but it also provides a rich source of observational data. By examining the various absorption lines in the X-ray and ultraviolet spectra, astronomers can piece together a 3D portrait of the wind's structure, its speed, thickness, and energy content. This kind of analysis has revealed another strange property. UFOs seem to have a preferred direction. They're not being blasted out in all directions equally. Instead, the winds are collimated, like jets, often perpendicular to the plane of the accretion disk. This suggests that strong magnetic fields are playing a crucial role, guiding the flow of plasma along specific paths. Some researchers propose that UFOs might be closely related to the relativistic jets we see in radiolud AGNs, just operating under different conditions or in different regions of the disk. It's also worth noting that these phenomena are not isolated to one type of galaxy. While quasars and Seyfert galaxies are the most common sources of UFO observations, similar outflows have been detected in ultraluminous infrared galaxies, ULIRGs, broad absorption line, BL, quasars, and even dormant or transitioning AGNs. This suggests that ultra-fast outflows are a universal phase in the life of galaxies, a kind of rite of passage that all massive galaxies go through as their central black holes feed, grow, and interact with their environments. Even more compelling is the role UFOs may play in black hole spin evolution. When matter falls into a black hole, it doesn't just increase its mass, it also contributes to its spin, depending on the direction of angular momentum. But if a powerful wind is launched from the disk and carries away that angular momentum before the matter reaches the event horizon, the black hole's spin could be slowed or stabilized. In other words, ultra-fast outflows might act as a natural regulator of black hole spin, keeping the system in balance and preventing it from reaching dangerously unstable configurations. This balance is important, because a rapidly spinning black hole can be incredibly efficient at converting mass into energy, sometimes extracting power directly from its rotation via mechanisms like the Blandford's-Najek process. If UFOs help modulate that spin, then they're essentially fine-tuning the entire energy output of the AGN, determining whether it's a gentle fountain or a raging inferno. That's a staggering level of influence for something as intangible as a wind of ionized gas. The ripple effects of UFOs don't stop at the galactic scale. There's growing evidence that these winds may also play a role in shaping the intergalactic medium, IGM, the diffuse gas that fills the vast voids between galaxies. As these outflows escape their host galaxies, they can carry metals and energy into the IGM, seeding it with the building blocks of future star systems and heating it in ways that influence cosmic structure formation. This kind of feedback isn't just galactic, it's intergalactic, extending the reach of black holes far beyond the boundaries of the galaxies that host them. And with next-generation telescopes like the James Webb Space Telescope, JWST, Athena, and Lynx on the horizon, the study of UFOs is about to enter a whole new era. These instruments will allow us to detect weaker winds, in more distant galaxies, and in higher detail than ever before. We may even begin to watch UFOs evolve in real time, catching the moment of ignition when an outflow is born or the slow fade as it dissipates into the void. The future of UFO research is rich with possibilities, and likely to reveal not only more mysteries but also answers to questions we haven't yet learned to ask. This variability allows astronomers to use ultra-fast outflows as real-time monitors of black hole behavior, giving us a rare chance to witness changes in a system that is otherwise hidden in darkness. Unlike stars, which radiate steadily for millions or billions of years, active galactic nuclei can flare up or dim dramatically in short spans of time, sometimes within just a few days or weeks. These sudden changes in brightness and outflow activity reveal a dynamic and ever-shifting environment. It's as if we're watching the heartbeat of a cosmic beast, irregular, forceful, and unpredictable. When the outflows intensify, it often correlates with an increase in the accretion rate, suggesting that the black hole is undergoing a feeding frenzy. On the other hand, when the winds weaken or disappear, it could mean the black hole has entered a temporary state of starvation, or that the wind's geometry has shifted out of our line of sight. The timescales on which UFOs vary can also teach us something about their proximity to the black hole. If a wind strengthens or weakens in just a few days, that implies it's being launched from a very compact region, possibly just a few light days from the event horizon. That, in turn, allows researchers to put constraints on the size and structure of the launching mechanism. This proximity also explains why UFOs are so tightly linked to the accretion disk itself. They are not some far-flung consequence of black hole activity. They are embedded in the central engine, part of the mechanism that controls the black hole's influence over its host galaxy. When scientists try to model these processes, they often turn to advanced computational simulations. These models attempt to replicate the extreme physics occurring near the event horizon, including magnetohydrodynamic, MHD, effects, relativistic fluid flows, and radiation pressure. These simulations have become increasingly sophisticated over the past decade, thanks to advancements in supercomputing. By inputting different parameters, such as black hole mass, spin rate, accretion disk temperature, and magnetic field strength, researchers can watch as winds form and evolve in virtual space. What's remarkable is how often these simulations reproduce structures that match what we see in real observations. This feedback loop between theory and data has led to a golden age in the study of ultra-fast outflows. A key takeaway from these simulations is that the strength and structure of a UFO depend heavily on the black hole's spin. A rapidly spinning black hole has a much more dynamic ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. This dragging effect, known as frame dragging, can amplify the magnetic fields threading through the accretion disk, giving rise to stronger and more organized winds. In fact, some models suggest that the most powerful UFOs can only be generated by black holes spinning near the maximum possible rate allowed by general relativity. If this is true, then the mere detection of a UFO could be a clue that the central black hole is spinning at extraordinary speed. What complicates matters is the role of orientation. The way we observe a galaxy, and by extension, its UFO, depends heavily on our viewing angle. If we're looking straight down the outflow's barrel, we might see a much stronger and more blue-shifted signal than if we're viewing it edge-on. This has introduced significant selection bias into UFO studies. We may be detecting only the most obvious and favorably aligned examples, while missing a much larger population of less visible outflows. Correcting for this bias requires statistical models and wide-ranging surveys that account for different galaxy types, orientations, and observational limits. As astronomers continue to refine these models, they are also discovering intriguing links between UFOs and other cosmic structures, such as jets. Unlike winds, which are relatively broad and thermal in nature, jets are narrow beams of relativistic particles launched at nearly the speed of light. For years, jets and winds were thought to be separate phenomena. However, new research suggests that they may share a common origin. In some cases, the inner part of the accretion disk may launch a tightly collimated jet, while the outer disk drives a broader, slower wind. The distinction between a UFO and a jet may therefore be one of degree rather than kind, two aspects of the same underlying process shaped by geometry, magnetism, and energy. This connection leads to a powerful insight. UFOs may serve as a missing link between black hole accretion and galaxy-scale feedback. While jets can punch holes through the galaxy and deposit energy in distant regions, UFOs interact more intimately with the galaxy's central environment. Their slower speeds and broader cross-section make them highly effective at disturbing the interstellar medium, inflating bubbles of hot gas, and displacing cold molecular clouds. In this way, UFOs are like the lungs of the black hole, breathing energy and motion into their surroundings with every pulse of activity. In recent years, researchers have also begun to explore whether UFOs might be connected to other extreme phenomena, such as tidal disruption events (TDEs). These occur when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. The resulting debris spirals into the accretion disk, triggering an intense flare and often launching winds and jets. Some scientists have speculated that the outflows seen in TDEs might resemble UFOs in both structure and speed. If true, this would suggest that UFO-like behavior is not limited to AGN but can arise in other high-energy contexts as well. This idea opens up a new avenue of study, one that could link disparate cosmic events through the common language of outflow dynamics. Meanwhile, in the observational domain, efforts are underway to improve the resolution and sensitivity of instruments used to study UFOs. The upcoming launch of next-generation X-ray observatories, like the European Space Agency's Athena mission or NASA's Lynx X-ray Observatory, promises to revolutionize our understanding of these winds. With higher resolution and better spectral coverage, these telescopes will be able to dissect the fine structure of UFO absorption lines, detect fainter outflows, and monitor their variability with unprecedented precision. It's an exciting time. Within a decade, we may have a vastly clearer picture of how UFOs operate, and what roles they play in the cosmic story. Beyond the physics and astrophysics, there is a poetic grandeur to ultra-fast outflows. They are the echoes of cosmic violence, the breath of invisible monsters dwelling at the hearts of galaxies. They embody the paradox of creation through destruction, the idea that stars may be born from the same winds that tear galaxies apart. In their speed, their power, and their mystery, they invite us to confront the fundamental forces that shape our universe. They are not merely a curiosity for specialists, they are a profound reminder that even in the cold vacuum of space, nature finds ways to move, to evolve, and to astonish. And as we peel back the layers of their secrets, we are not just learning about black holes or galaxies, we are learning about ourselves. For in every spectrum line, in every burst of X-rays, and in every model of accretion physics, we are chasing a deeper truth. One that speaks not just of matter and energy, but of the hunger to know. The same hunger that drives black holes to feed may also drive the human mind to understand. And in that, perhaps, we find a reflection of the universe's own restless, reaching spirit. By adjusting variables such as black hole mass, accretion rate, magnetic field strength, and disk thickness, they can observe how the outflows respond. Some of the most successful models suggest that UFOs arise when the intense radiation from the accretion disk pushes against the infalling material, while magnetic fields thread through the disk and help accelerate the gas outward in a collimated stream. The balance between radiation pressure and magnetic tension seems to be a critical factor in determining the speed, direction, and intensity of the resulting wind. One of the most intriguing revelations from these simulations is that ultra-fast outflows might actually act as self-regulating feedback loops. As the wind blasts away surrounding gas and dust, it can limit the black hole's own supply of fuel, thereby reducing the accretion rate and calming the outflow. But once the surrounding material settles again, the cycle can restart. This process may help explain why most galaxies, including our own, have supermassive black holes that seem to sleep for long periods of time, occasionally awakening with short bursts of activity. It's as if the UFO is not just a product of the black hole, it's also a mechanism that keeps the black hole in check, like a thermostat regulating cosmic temperature. In recent years, observations have shown that UFOs may also play a critical role in shaping the circumgalactic medium, the vast halo of gas that surrounds galaxies. This diffuse region acts as both a reservoir and a recycling bin for galactic material. As the outflows smash into this medium, they can heat it, stir it, and even seed it with heavy elements forged near the black hole. This process not only alters the chemical composition of the halo but can also affect the future growth of the galaxy itself. For example, if the halo becomes too hot or turbulent, it may prevent cool gas from condensing and falling into the galactic center, effectively shutting off star formation. Moreover, recent X-ray observations from telescopes like XMM Newton and Chandra have uncovered tantalizing clues about the composition of UFOs. While we know they are largely made of ionized gas, their exact makeup varies depending on the AGN. Some winds are rich in iron, while others contain traces of silicon, oxygen, and neon. These chemical fingerprints help astronomers understand the nuclear processes taking place near the event horizon. For instance, an excess of certain elements might indicate past episodes of intense star formation, or even supernova explosions near the galactic core. These observations serve as forensic tools, allowing scientists to reconstruct the history of black hole activity and the evolution of its host galaxy. Interestingly, UFOs are not only present in high-luminosity quasars or massive ellipticals. They've also been detected in relatively low-mass galaxies and even intermediate-mass AGNs, which suggests that these outflows are a universal phenomenon, not limited by the scale of the galaxy or the size of its central black hole. This universality further supports the idea that UFOs are an intrinsic part of black hole growth and galactic feedback, rather than a rare or exotic occurrence. It also implies that our own Milky Way, whose supermassive black hole, Sagittarius A*, is currently dormant, may have once experienced similar outflows in its more active past. Another fascinating aspect of ultra-fast outflows is their potential to illuminate the mysterious connection between dark matter and visible matter. While dark matter doesn't interact with electromagnetic radiation, it does respond to gravitational influences. The forceful ejection of gas by UFOs could theoretically shift the distribution of baryonic matter in a galaxy, and this, in turn, might affect how dark matter clumps and moves. While this idea is still speculative, it opens a tantalizing door into one of cosmology's greatest puzzles. How do black holes influence not just the visible structure of the universe, but its hidden scaffolding as well? Furthermore, as technology continues to improve, particularly with the upcoming launch of next-generation observatories like the Athena X-ray telescope and the Lynx mission, we can expect a revolution in our understanding of UFOs. These telescopes will offer unprecedented resolution and sensitivity, allowing us to probe the fine structure of outflows in greater detail than ever before. We will be able to map the wind's velocity field, temperature gradient, and ionization state with exquisite precision. This level of detail may finally allow scientists to test competing theories about the wind's origin, and to determine once and for all whether radiation, magnetic fields, or some yet unknown mechanism is the true driver behind these cosmic hurricanes. And yet, for all we are learning, UFOs continue to elude complete explanation. Every time we uncover a new detail, be it a surprising velocity measurement, a novel chemical signature, or a sudden disappearance from the sky, it raises as many questions as it answers. Why do some AGNs launch UFOs while others remain quiet? What triggers the onset of an outflow, and what determines its lifetime? How does the presence of a companion galaxy, a central starburst, or a dense galactic core influence the wind's properties? These are not just technical questions, they are windows into the cosmic ballet of matter and energy that governs everything from star formation to galaxy collisions. Ultra-fast outflows may prove to be the missing link between small-scale physics and large-scale structure. They emerge from the extreme environment of the black hole's inner region, where Einstein's relativity meets quantum mechanics, and extend their influence across tens of thousands of light-years, shaping the fate of entire galaxies. In this sense, they are the bridge between the micro and the macro, between the chaos of the quantum world and the elegance of cosmic evolution. If the circumgalactic medium becomes too hot and turbulent, it can delay or prevent the recycling of gas back into the galaxy, effectively starving it of the raw materials needed for star formation. In this way, ultra-fast outflows are not merely local phenomena, they are galactic architects, shaping star formation rates, chemical enrichment, and the very life cycle of matter in the universe. The extreme temperatures associated with UFOs, often tens of millions of degrees Kelvin, also give rise to some of the most energetic radiation known to science. X-ray telescopes such as NASA's Chandra X-ray Observatory and ESA's XMM Newton have been essential tools in detecting and analyzing these outflows. These observatories can spot the subtle blue shifts in absorption lines from highly ionized atoms like iron, silicon, and oxygen, which betray the presence of material moving at relativistic speeds toward us. These blue shifted lines provide not just confirmation of the outflow's existence, but also clues about their composition, density, and structure. Each line is like a fingerprint, uniquely identifying the elements present in the flow and the physical conditions they endure. What's more, the detection of UFOs across a broad range of AGN types suggests that they are a common, perhaps universal, feature of supermassive black holes. Whether the black hole is a few million or a few billion solar masses, whether it's in a spiral or elliptical galaxy, the same kind of ultra-fast, ultra-energetic wind seems to arise when the conditions are right. This universality strengthens the argument that UFOs are not anomalies, but fundamental elements of galactic evolution. They may be as essential to the cosmic ecosystem as supernovae, black holes, and dark matter. And yet, there is a paradox at the heart of our understanding. Despite their violence and intensity, ultra-fast outflows are often invisible to most wavelengths of light. We don't see them glowing brightly in visible or infrared. They reveal themselves mainly through what they block or shift in the X-ray spectrum. This makes them elusive, ghost-like entities that haunt the surroundings of black holes. Their detection requires precision instruments, careful timing, and sophisticated data modeling. One might say that they exist more in their absence than in their presence, not in what they emit, but in what they obscure. This quality has led some researchers to draw poetic comparisons between UFOs and the winds of fate, forces that are invisible, uncontrollable, and yet capable of altering destinies. These cosmic winds shape galaxies over billions of years, deciding where stars will be born and where they won't, which galaxies will thrive and which will fade. It's a reminder that not all power is visible. Some of the most significant forces in the universe operate in shadow and silence, bending the arc of cosmic history with a whisper rather than a roar. As our telescopes grow more sensitive and our simulations more sophisticated, new layers of complexity continue to emerge. Some models now suggest that UFOs may interact with slower, cooler outflows at greater distances, creating complex multi-phase wind systems. In these systems, ultra-fast hot gas carves through more massive but slower-moving material, creating shock fronts, turbulence, and perhaps even sites for molecule formation in their wake. These interactions could enrich the surrounding space with heavy elements, seeding future star systems with the ingredients for planets and life. The implications of UFOs don't stop at galaxies. They may also have a role in the grander tapestry of cosmic evolution. By regulating black hole growth and galactic development, they influence large-scale structure formation, cluster dynamics, and even the distribution of matter across the universe. In essence, these outflows, born in the fiery hearts of galaxies, ripple outward through time and space, echoing across the cosmic web. Yet, despite all this progress, many questions remain. We still don't fully understand the trigger mechanisms. What precise conditions flip the switch that turns a quiet black hole into a cosmic blowtorch? Nor do we fully grasp the long-term life cycle of a UFO. Are they born, live, and die like stars, or do they flicker in and out of existence like ghosts, tethered to the chaotic whims of their parent black holes? Some theorists even propose that there might be multiple types of UFOs, distinguished by their launch mechanisms: radiation-driven, magnetically driven, or perhaps combinations of both. Each new discovery nudges us closer to the answers, but the mystery remains tantalizing. We are staring into a cosmic forge, watching winds blow with the strength to sculpt galaxies, and yet we still do not fully comprehend the forces at play. This is the beauty of space mysteries. They don't just ask questions. They invite us to grow, to explore, and to imagine what might lie beyond the veil of what we currently know. As ultra-fast outflows carve through the circumgalactic medium, they do more than just disrupt. They imprint structure, shocking gas into filaments, generating turbulence, and initiating chemical mixing. The trails they leave behind can remain visible for eons, like scars etched into the galactic halo. This process may be responsible for the formation of certain high-energy emission regions observed in distant galaxies, zones where matter has been compressed and ionized to the point that it glows in exotic ultraviolet and X-ray wavelengths. These luminous relics act as cosmic signatures, whispering stories of past outbursts from long-dormant galactic cores. Astrophysicists have long theorized that such feedback mechanisms are essential for explaining several galactic mysteries, such as why massive galaxies stop forming stars so early in their lives, or why black hole mass appears to be tightly correlated with the bulge mass of their host galaxies, a relationship known as the M-sigma relation. Ultra-fast outflows could be the missing link. By regulating gas inflow and triggering shockwaves that propagate throughout galactic structures, UFOs may be directly responsible for sculpting the observable properties of galaxies across cosmic time. The correlation between black hole growth and galaxy evolution has puzzled scientists for decades. After all, a supermassive black hole is a tiny fraction of its host galaxy's mass, yet it somehow exerts immense influence over the entire structure. Ultra-fast outflows, launched at velocities exceeding 10% of the speed of light, provide a viable explanation. Even though the black hole itself is small in physical scale, the energy it releases through accretion and subsequent outflows is so intense that it can influence regions thousands of light years across. It's a case of a small agent producing a massive impact, a David among galactic Goliaths. Interestingly, some UFOs appear to exhibit a phenomenon known as multiphase structure. This means that the outflow isn't composed of a single uniform stream of gas but instead consists of multiple layers or zones, each with different temperatures, densities, and ionization states. Imagine an onion-like structure of material, dense, cooler cores surrounded by hot, highly ionized envelopes, racing outward from the galactic nucleus. This complexity adds further depth to the mystery, suggesting that the launching and acceleration mechanisms may be even more nuanced than previously imagined. Multiphase winds may arise from stratified accretion disks or from instabilities within the wind itself, such as turbulence or magnetic reconnection. A critical observational tool in decoding these structures is the measurement of absorption variability. By monitoring how the strength and profile of absorption lines change over time, researchers can infer the physical conditions within different zones of the outflow. In some cases, they've observed rapid fluctuations in the absorption features, on timescales as short as a few hours, implying that the outflowing material is incredibly close to the black hole, perhaps just a few light hours away. These time-resolved studies offer a sort of weather map of the environment surrounding the black hole, tracking clouds and streams of ionized gas as they traverse our line of sight. In more advanced cases, reverberation mapping techniques have been employed to probe the three-dimensional structure of these outflows. By analyzing the time delays between X-ray continuum emissions and their reprocessed echoes in various absorption or emission lines, astrophysicists can reconstruct the geometry and kinematics of the material around the black hole. These time lags act like sonar pings, bouncing off different layers of gas and revealing the contours of the invisible structures that lie within the heart of the AGN. Beyond X-rays, future explorations of ultra-fast outflows are poised to expand into the realm of multi-wavelength astronomy. Instruments that detect infrared, ultraviolet, and even radio emissions are being used in tandem with X-ray observatories to gain a fuller picture of these complex systems. Each wavelength regime offers a unique perspective. While X-rays expose the hottest and most energetic regions, infrared data can track the cooler dust that might be entrained in the outflows, and radio telescopes can reveal synchrotron emissions from electrons spiraling around magnetic fields. By integrating data across the spectrum, scientists hope to untangle the physical processes at play with greater clarity than ever before. One particularly tantalizing area of study is the connection between ultra-fast outflows and cosmic rays. These high-energy particles, primarily protons and atomic nuclei, zip through space at nearly the speed of light, yet their origins remain poorly understood. Some theorists propose that UFOs could be natural particle accelerators, boosting charged particles to tremendous energies as they interact with shocks and magnetic fields within the outflow. If confirmed, this would establish a direct link between the chaotic centers of galaxies and the energetic radiation that bombards our planet from space. The potential connection to cosmic rays opens new doors for experimental physics as well. Ground-based observatories like the Pierre Auger Observatory and the Cherenkov Telescope Array may be able to detect signatures of particle acceleration linked to distant AGN. If these observatories can correlate high-energy particle events with known outflows from specific galaxies, it would strengthen the hypothesis that UFOs serve as the cosmic slingshots hurling energetic matter across the universe. This could unify phenomena once thought unrelated: galactic feedback, particle physics, and even interstellar chemistry. Then there's the question of magnetic topology, the configuration of magnetic field lines in and around the accretion disk. These magnetic fields are not static. They twist, fold, and reconnect, especially under the influence of the black hole's intense gravitational and rotational energy. Magnetohydrodynamic simulations show that this dynamic magnetism can funnel gas into tight spirals and form narrow channels through which material is launched at incredible speeds. These magnetically driven jets can either work in tandem with radiation-driven winds or independently, depending on the black hole's spin and the configuration of the disk. Some models suggest that the fastest UFOs are those where magnetic acceleration dominates, creating tightly collimated streams capable of traveling far beyond the host galaxy's halo. On the observational front, polarimetry is emerging as a new technique to explore the magnetic nature of ultra-fast outflows. By measuring the orientation and degree of polarization in light from AGN, astronomers can infer the structure of magnetic fields that influence the outflows. Future missions equipped with advanced X-ray polarimeters may offer direct insights into the magnetic geometry of these winds, allowing us to distinguish between competing theories of wind formation and propagation. The evolution of ultra-fast outflows over cosmic time is another area of deep interest. Are UFOs more common in the early universe, when black holes were growing rapidly? Or are they a consistent feature across all epochs? Large-scale surveys of quasars, extremely luminous AGN from the early cosmos, are helping answer this question. Some studies suggest that UFO activity peaked several billion years ago, coinciding with the most active phase of black hole growth. If true, then UFOs may have played a starring role in shaping the universe as we see it today, regulating early star formation, influencing galaxy mergers, and contributing to the metal enrichment of intergalactic space. Between black hole mass and galactic bulge velocity dispersion, known as the M-sigma relation, suggests a deep, perhaps even causal, connection between the evolution of a black hole and the galaxy surrounding it. But this correlation is perplexing if one considers the scale differences involved. A black hole, even 1 billionth of times the mass of the Sun, is still minuscule compared to its host galaxy. How can something so comparatively small exert such immense influence? Ultra-fast outflows offer a compelling answer. By injecting vast amounts of momentum and energy into the galactic ecosystem, they become agents of balance, ensuring that the growth of the black hole does not outpace the needs or stability of its host. This feedback, however, is not always neat or controlled. In some AGNs, UFOs become chaotic, tearing apart entire swaths of molecular clouds and ejecting gas into intergalactic space. This violent expulsion leaves behind regions starved of the essential ingredients for stellar formation. Galaxies that once blazed with the brilliance of starbirth can quickly fade into red, quiescent shadows of their former selves. These red and dead galaxies puzzle astronomers because their star formation shuts down long before their gas supply is fully depleted. UFOs, with their blistering energy and sweeping winds, might be the unseen assassins responsible. The possibility that ultra-fast outflows are responsible for quenching star formation on galactic scales has opened new doors in cosmological modeling. Simulations like Illustris and Eagle now incorporate feedback modules specifically accounting for AGN-driven winds. These virtual universes have shown remarkable success in reproducing key observations from our own universe, things like the distribution of galaxy types, their mass functions, and the metallicity of intergalactic gas. Without UFO feedback, many of these results fall apart, leading to unrealistically overgrown galaxies and far too much star formation in the early universe. Yet, for all the progress that's been made, UFOs still harbor secrets. One major question that continues to haunt astronomers is what determines the onset of these outflows. Why do they erupt suddenly in some galaxies and remain dormant in others, even when black holes of similar mass are present? Some believe that the answer lies in the configuration of the accretion disk, particularly in the stability of its magnetic field. A magnetic field that becomes twisted or sheared may reach a critical threshold and unleash a jet-like eruption of material. Others argue that it's more about the fuel. When a sudden inflow of cold gas reaches the black hole, it triggers a brief but intense feeding frenzy, leading to the generation of a UFO. Another intriguing theory posits that UFOs might be cyclical in nature, governed by a feedback loop involving star formation, gas inflow, and black hole activity. In this model, a galaxy undergoes a burst of star formation that also feeds the central black hole. The increased accretion lights up the AGN, which in turn launches a powerful UFO. This outflow disrupts further star formation and chokes off the black hole's fuel supply, causing both processes to shut down. Over time, as the galaxy settles and gas reaccumulates, the cycle begins again. If true, this would paint a picture of galaxies as dynamic, self-regulating systems, where stars and black holes co-evolve in a delicate dance orchestrated by invisible winds. What's even more astonishing is the recent suggestion that UFOs might not be purely baryonic in nature. Some studies have begun to explore whether these outflows could contain components of dark matter, or at least interact with it in a way that influences its distribution. This is still speculative, but if true, it would provide an unprecedented window into the invisible side of the universe. Observations of gravitational lensing near active galactic nuclei hint at disturbances that some researchers believe could be caused by UFOs interacting with the surrounding dark matter halo. Even more mystifying are the signals that UFOs leave behind in the cosmic web. Vast filaments of gas that stretch between galaxies appear to glow more brightly near AGNs. Could this be the fingerprint of UFOs energizing the intergalactic medium? Some scientists think so. By energizing gas across cosmic scales, these outflows may not only be responsible for shaping galaxies, but for illuminating the very structure of the universe itself. Their reach may extend far beyond what we previously imagined, seeding the cosmic landscape with momentum and turbulence in ways we are only beginning to understand. The technology used to detect these subtle phenomena is equally mind-blowing. Next-generation X-ray telescopes like Athena, Advanced Telescope for High-Energy Astrophysics, set to launch in the coming years, promise unprecedented sensitivity and resolution. These instruments will allow astronomers to not only detect UFOs more easily, but to map their internal structure in exquisite detail. For the first time, we'll be able to visualize how these winds evolve in real time, how they start, how they grow, and how they fade. This could finally answer some of the most persistent questions about their origin, composition, and life cycle. Another cutting-edge development involves polarimetry, the measurement of the polarization of X-rays emitted by UFOs. By studying how the orientation of these rays changes as they pass through magnetic fields and ionized gas, scientists can reconstruct a kind of three-dimensional map of the outflow. This is crucial for understanding their geometry, something that is currently inferred only indirectly. Knowing the exact shape and orientation of a UFO will help determine its true velocity and energy content, two of the most critical parameters in understanding their role in galactic evolution. And then there are the potential links to gravitational waves. Some theoretical models suggest that the same instabilities that trigger UFOs could also cause minor fluctuations in space-time, tiny ripples that, while far weaker than those produced by merging black holes, could still be detectable with next-generation observatories. If proven, it would add an entirely new observational dimension to the study of these outflows, allowing us to listen to them as well as see them. Some of the most breathtaking examples have come from quasars, the hyperluminous cousins of typical AGNs. These celestial powerhouses are bright enough to be seen across billions of light-years, acting like cosmic lighthouses in the deep night. In some of the closest and brightest quasars, astronomers have detected UFOs tearing through the surrounding gas at speeds exceeding 30% the speed of light. These jets are not narrow beams like those seen in radio galaxies. They are wide-angle winds, broad and turbulent, suggesting a chaotic ejection of material rather than a precision-engineered blast. One of the most stunning observations came from the quasar PDS 456, located about 2 billion light-years from Earth. Using both XMM Newton and NuSTAR, astronomers detected highly ionized iron moving outward at roughly 0.3 C, nearly 100,000 kilometers per second. The sheer power of this outflow is staggering. If sustained, it could eject more than 10 solar masses of material per year from the galactic core. This isn't just a breeze from the black hole, it's a hurricane powerful enough to alter the fate of an entire galaxy. Yet not all UFOs are this extreme. Some are more subtle, whispering instead of roaring. These quieter outflows can still deliver feedback, but in gentler doses, allowing for cycles of gas inflow and outflow that sustain a galaxy's star formation for longer periods. This duality has led scientists to consider that there may be multiple UFO modes, one for violent quenching and one for steady regulation. The precise trigger for switching between these modes is still unknown, but it may depend on the black hole's accretion rate, magnetic field configuration, or even the angular momentum of the surrounding gas. Magnetohydrodynamic simulations have added fuel to these speculations. These simulations model how magnetic fields interact with rotating, ionized gas around the black hole. In some configurations, magnetic pressure builds up until it exceeds the force of gravity and drives material outward in a sudden, explosive release, an ultra-fast outflow. In others, magnetic fields guide gas into smoother, less violent flows. Understanding which magnetic geometries produce which outflow types is an active area of research and could unlock the mystery of why some AGNs blast their surroundings with fury while others remain eerily quiet. There is also a rich interplay between UFOs and cosmic dust. Though UFOs are usually detected via X-ray observations of hot, ionized gas, they often plow through cooler, dusty regions as they expand outward. This interaction can destroy dust grains, release complex molecules, and even trigger new star formation by compressing otherwise stable gas clouds. Paradoxically, a destructive outflow might create pockets of creation along its fringes, seeding new stars even as it extinguishes others. These ripple effects are difficult to predict, making the impact of UFOs far more complex than initially assumed. In some cases, astronomers have found spatial correlations between UFOs and narrow-line emission regions several kiloparsecs away from the AGN core. These distant structures may be fossil echoes, relics of past outflow activity that carved their way through the galaxy long ago. The fact that they remain visible suggests that UFOs may not be fleeting phenomena but rather intermittent, recurring events that leave lasting imprints on galactic anatomy. These outbursts could happen every few million years, shaping the galaxy layer by layer across cosmic time. An even more tantalizing question is whether ultra-fast outflows can propagate beyond the galactic halo and into the intergalactic medium. If so, they may play a role in one of the most significant processes in the universe, the enrichment of the cosmic web. The diffuse gas that stretches between galaxies is not just hydrogen and helium, it's laced with heavier elements like carbon, oxygen, and iron. Where did these elements come from? Supernovae are one source, but UFOs, capable of ejecting chemically enriched gas at high velocity, may be another, spreading the products of star formation far and wide. Some theorists even speculate that UFOs could serve as agents of galactic communication. Not in the sense of intelligence, of course, but in the way they redistribute mass and energy. A particularly powerful outflow could collide with neighboring gas clouds, igniting star formation not only in its own galaxy but perhaps in satellites or neighboring systems. If confirmed, this mechanism would add an entirely new layer to our understanding of galaxy clusters, where one active nucleus could ignite a chain reaction across several galaxies. Despite decades of research, many questions remain unanswered. What exactly triggers a UFO? Why do some AGNs host them while others do not? How does the internal geometry of the black hole's accretion disk influence the shape and strength of the outflow? And can we ever hope to detect the full structure of a UFO, its origin point, acceleration profile, and outer limits, in a single, coherent observation? These are not just idle curiosities. Answering them could reveal the fundamental mechanics of how galaxies grow, live, and die. Fortunately, the future looks bright. New generations of observatories, like the upcoming Athena X-ray telescope from the European Space Agency and the Lynx X-ray Observatory concept from NASA, are designed with UFOs in mind. These instruments will offer unprecedented resolution, sensitivity, and spectral accuracy, allowing scientists to peel back layers of complexity that are currently hidden. With them, we may finally chart the full life cycle of ultra-fast outflows, from their birth in the accretion disk, to their journey through the galaxy, and perhaps even to their fading footprints in the cosmic web. What makes these outflows even more compelling is the degree to which they can influence not just the host galaxy, but also the vast intergalactic medium beyond. As these supersonic winds rip through the galactic core, they don't stop at the edge of the bulge or disk. They can continue pushing material outward for tens, sometimes hundreds of thousands of light years, interacting with satellite galaxies, triggering star formation in some pockets while stripping other regions clean. This interaction between the outflow and the surrounding environment creates vast shock fronts, some of which may persist for millions of years, acting like cosmic fossils of violent past events. The reach of a single AGN event, it turns out, can have ramifications far beyond what was once imagined. The energy required to drive such outflows is staggering. In many cases, a significant fraction of the accretion energy of the supermassive black hole, sometimes up to 10% of the mass energy of the infalling material, is funneled into these winds. That may not sound like much, but when you're dealing with black holes that consume several solar masses per year, even a small fraction of that energy becomes utterly titanic. We're talking about outputs rivaling the total luminosity of an entire galaxy, focused not into light, but into momentum, heat, and raw kinetic force. It's the closest nature comes to weaponizing gravity itself. The mechanism by which this energy is transferred is still the subject of intense study. Radiation pressure appears to play a primary role. As photons emitted from the inner regions of the accretion disk bombard the surrounding material, they push against it with tremendous force. This is especially effective in regions dense with ions, such as iron, silicon, and oxygen, which absorb high-energy photons more readily. Once this gas reaches a critical density and temperature, it is launched outward with near-relativistic speeds. But radiation pressure alone might not tell the whole story. Magnetic fields, emerging from the chaotic plasma environment near the event horizon, may further accelerate these winds through magneto-hydrodynamic processes that are only just beginning to be modeled in detail. This intersection of radiation, plasma, and magnetic force creates a volatile environment, one where instabilities can form, collapse, and regenerate with astonishing speed. These instabilities may explain why UFOs often appear clumpy or segmented in observational data. Instead of a smooth, continuous wind, what we're seeing could be a roiling ocean of turbulent eddies, shock fronts, and plasma bubbles expanding outward in unpredictable patterns. This chaos is one reason why it's difficult to track a UFO's structure over time. It may change dramatically in just a few years, a blink of an eye on cosmic scales. What's more, ultra-fast outflows don't simply vanish into the void once expelled. Over time, they cool, fragment, and interact with whatever gas lies in their path. In galaxy clusters, for instance, these winds may collide with intracluster media, creating secondary shockwaves that stir up the hot gas permeating the space between galaxies. This interaction can enrich the medium with metals, elements forged in the hearts of stars and now flung across light years by the force of a black hole's fury. In this way, black holes may serve as unlikely agents of cosmic recycling, spreading the building blocks of future stars and planets far and wide. Yet, the most tantalizing aspect of UFOs may be their ability to regulate cosmic timing. In younger galaxies, where star formation is rampant and gas is plentiful, ultra-fast outflows may serve to suppress or delay further growth, giving the galaxy time to stabilize. In older systems, the same winds might reignite star formation by compressing gas clouds on the periphery. The balance between these effects, quenching and triggering, is delicate, and likely varies from one galactic environment to another. This makes UFOs not just destructive forces, but potentially creative ones, capable of orchestrating the life cycles of entire stellar populations. The consequences of these outflows extend even to cosmic reionization. During the universe's earliest epochs, most of the matter existed in a cold, neutral state. But as the first stars and black holes ignited, they began to reionize this gas, making the universe transparent to light once more. It's possible that AGN winds, including UFOs, played a role in accelerating this transition. Their high-energy photons, coupled with the vast reach of their outflows, may have acted as cosmic bellows, blowing away the fog of neutrality and heating the surrounding regions to temperatures that enabled reionization to spread more efficiently. Observationally, these possibilities are just now coming into focus thanks to advanced instruments like the Chandra X-ray Observatory, ALMA, and James Webb Space Telescope. With greater spectral resolution and sensitivity, astronomers can dissect the line profiles of various ions to measure the speed, density, and composition of these outflows. Newer techniques like reverberation mapping and velocity-resolved spectroscopy allow us to track the motion of these winds in real time, or as close to real time as cosmic distances allow. These data sets are now feeding into AI-driven simulations that attempt to replicate outflow behavior across thousands of galactic scenarios. But there are still mysteries we haven't cracked. For example, why do some AGNs exhibit ultra-fast outflows while others, with seemingly similar masses and accretion rates, remain comparatively quiet? Could it be that UFOs are transient, blazing forth only during specific evolutionary stages of a galaxy? Or are we missing a key observational parameter, perhaps a hidden angle or frequency at which these winds reveal themselves? The answers may lie in phenomena we haven't yet linked to UFOs, such as certain fast radio bursts, gamma-ray flares, or unusual galactic structures that don't quite fit within traditional formation models. Additionally, there is a growing suspicion among some astrophysicists that ultra-fast outflows may contribute to the creation of intermediate-mass black holes. As these winds compress matter in dense galactic environments, they may seed the rapid collapse of gas clouds under extreme pressure. If these clouds are massive enough, they may skip the star formation phase entirely and collapse directly into black holes themselves. This would offer one potential solution to the long-standing puzzle of how black holes between stellar and supermassive sizes, those in the 100 to 100,000 solar mass range, come to exist. Equally fascinating is the idea that these outflows could be influencing dark matter halos, not through direct interaction, since dark matter doesn't couple with electromagnetic forces, but through gravitational reshaping. As UFOs push baryonic matter outward, they change the distribution of visible mass in a galaxy. This redistribution can alter the gravitational potential well, potentially leading to subtle shifts in the configuration of the surrounding dark matter. If proven, it would mean that black hole feedback loops affect not just the luminous universe, but also the invisible skeleton that holds it together. Radiation pressure appears to play a major role, particularly in systems where the accretion disk around the supermassive black hole shines near or above its Eddington limit. When the black hole is consuming matter at an intense rate, the resulting light exerts outward pressure on the surrounding gas, accelerating it outward. But this radiation pressure isn't uniform. It acts selectively on certain ionized particles, especially those with strong absorption lines like iron, oxygen, and silicon. These atoms absorb X-ray and ultraviolet photons with high efficiency, heating up and expanding violently. As the gas becomes more ionized, it becomes transparent to radiation, complicating the flow dynamics and making the entire process a delicate balance between momentum transfer, ionization state, and the geometry of the outflow itself. There is also growing evidence that magnetic fields contribute significantly to the launch of these outflows. Some models propose a magnetocentrifugal mechanism, where magnetic field lines anchored to the spinning accretion disk act like slingshots, flinging particles outward as the disk rotates. These magnetically driven winds can maintain their structure over vast distances, possibly explaining why some outflows are collimated into broad cones or bipolar shapes. Unlike purely radiatively driven winds, magnetic outflows can originate closer to the event horizon and may be less susceptible to ionization saturation, allowing them to remain stable even in highly energetic environments. As these ultra-fast outflows accelerate outward, they don't travel through empty space. They slam into the interstellar medium, ISM, creating vast bow shocks and turbulence that can completely transform the host galaxy. Cold gas clouds, which would normally collapse to form stars, are shredded by the passing winds or compressed into high-density filaments. In some cases, this compression may trigger short-lived bursts of star formation along the edges of the outflow cone, an effect observed in certain Seyfert galaxies. But over time, the dominant outcome is often suppression, as the wind's energy injects heat and disorder into the ISM, halting further collapse and shutting down the galactic assembly line. This turbulent interplay between outflows and the ISM creates a complex, layered structure in the heart of active galaxies. Observations with integral field spectrographs have revealed nested zones of gas moving at different velocities and temperatures. Closer to the black hole, we see ultra-ionized elements racing outward at relativistic speeds. Further out, partially ionized clouds are caught in the blast wave, their velocity gradients mapping the flow of energy through the galactic core. At even greater distances, neutral hydrogen and molecular gas form shocked shells and filaments, glowing faintly in infrared as they slowly cool. This entire system acts like a feedback engine, self-regulating the growth of the black hole and the galaxy in a chaotic, yet strangely coordinated dance. The consequences of these outflows ripple far beyond the host galaxy. When the expelled gas reaches the circumgalactic medium, CGM, the diffuse envelope of material that surrounds a galaxy, it can enrich it with metals and inject turbulent motion that lasts for eons. Some of the material may even escape into the intergalactic medium, IGM, carrying signatures of the galaxy's inner life out into the void. These metal-rich regions can later seed the formation of new stars and galaxies, suggesting that AGN winds are not merely destructive but also generative, recycling matter across cosmic scales. In fact, the metallicity of the intergalactic medium is one of the strongest clues that something violent and far-reaching is at play. Observations of the Lyman alpha forest, absorption lines in the spectra of distant quasars caused by intervening hydrogen, have shown that even remote regions of the universe contain traces of heavy elements. Since these metals can only be forged in stars and dispersed by extreme forces, UFOs and other AGN-driven outflows become likely culprits. They provide a mechanism by which galaxies pollute their surroundings, spreading the ashes of stellar evolution across the cosmic web. The broader implications of this process stretch into the field of galaxy evolution. The balance between inflow and outflow determines not just the galaxy's morphology, but also its lifespan. A galaxy that experiences multiple intense outflows may transition rapidly from a star-forming spiral to a passive elliptical. The central black hole, through its AGN activity, dictates the galactic life cycle, deciding whether it remains a vibrant stellar nursery or fades into quiescence. This kind of internal regulation has reshaped how astronomers view the role of supermassive black holes, not as passive sinks of mass, but as active agents of cosmic engineering. Even more intriguing is the idea that UFOs might influence large-scale structure formation itself. In galaxy clusters, where thousands of galaxies reside in a dense environment filled with hot plasma, AGN feedback appears to prevent catastrophic cooling. Without such outflows, the intracluster medium would lose energy rapidly, collapsing under its own weight and triggering a runaway burst of star formation in the central galaxies. But thanks to these violent winds and jets, the cooling is moderated, maintaining a quasi-stable environment for billions of years. This maintenance mode is critical to the observed properties of galaxy clusters, and ultra-fast outflows may be one of the key contributors. Astronomers are now pushing the limits of instrumentation to capture these outflows in even greater detail. Future missions like Athena, Advanced Telescope for High-Energy Astrophysics, promise unprecedented resolution in the X-ray regime, allowing scientists to dissect the structure of UFOs with exquisite precision. Coupled with next-generation observatories like the James Webb Space Telescope and the Extremely Large Telescope, we will soon be able to map the full life cycle of AGN winds, from their birth near the event horizon to their final dispersal into the cosmic abyss. These instruments will help answer pressing questions about their launch mechanisms, compositions, and long-term effects. All of this points to a larger realization that ultra-fast outflows are not rare anomalies, but essential components of the cosmic ecosystem. They are not accidents or edge cases, they are fundamental. Wherever there are growing black holes, there are outflows. Wherever galaxies evolve, they do so under the pressure of these winds. They connect the very small, the physics of black hole accretion, with the very large, the dynamics of galaxy clusters and the structure of the universe itself. It's a testament to how interconnected everything is, from the depths of singularities to the voids between galaxies. What once seemed like peripheral noise, high-velocity gas that appeared as odd features in X-ray spectra, is now central to our understanding of cosmology. The more we study ultra-fast outflows, the more they appear not just as side effects, but as sculptors of galaxies, regulators of matter, and engines of cosmic change. They are the invisible architects shaping our universe across time and space. As these ultra-fast outflows accelerate outward, they don't travel through empty space. They slam into the interstellar medium surrounding the galactic nucleus, creating shock waves that can heat gas to tens of millions of degrees. These collisions compress and stir the gas, sometimes triggering bursts of star formation, but more often disrupting the delicate clouds from which stars would otherwise form. The result is a galaxy-wide suppression of star birth, AGN feedback in its rawest, most violent form. It's a cosmic paradox, a supermassive black hole that fuels incredible radiance, and energy becomes the very force that quenches the life of the galaxy around it. The timing of these events is equally important. Ultra-fast outflows are not constant, steady winds. They occur in episodes, bursts of fury that can last thousands to hundreds of thousands of years. In cosmological terms, these are brief flashes. But during that time, the AGN can carve out massive cavities in the gas-rich central regions of the galaxy. Once the fuel supply dwindles or the black hole stabilizes, the AGN quiets down and the outflow fades. But the scars remain: heated gas reservoirs, disrupted molecular clouds, and an altered interstellar environment that may take millions of years to return to equilibrium. Observationally, tracing these outflows has become one of the primary missions of modern X-ray and UV telescopes. Instruments like Chandra, XMM Newton, and new star have enabled astronomers to detect the telltale blue shifted absorption lines that signify gas moving toward us at extraordinary speeds. These signatures often come from highly ionized iron, particularly Fe-XXV and Fe-XXVI, and appear as broad, asymmetric troughs in the X-ray spectrum. The width and depth of these lines provide clues about the density, temperature, and velocity of the wind. In some cases, we see multiple absorption zones at different velocities, suggesting layered structures in the outflow. One of the more fascinating aspects of these winds is their geometry. Unlike narrow jets, ultra-fast outflows often emerge in wide-angle cones, affecting a large portion of the host galaxy. This geometry is crucial. It determines how much mass and energy the outflow can carry away and how broadly its influence is felt. In simulations, wide-angle winds are far more effective at quenching star formation than tightly collimated jets, which often pierce through the interstellar medium with less interaction. The shape and reach of these winds can dictate the fate of entire galactic populations. Even the chemical enrichment of galaxies, and the intergalactic medium beyond, may depend on these flows. As gas is ejected at high speeds, it carries with it the heavy elements produced in stellar furnaces and supernovae. These metals are dispersed into the halo of the galaxy, and in some cases, beyond it, seeding the surrounding space with the raw ingredients for new stars and planets. Without this dispersal mechanism, heavy elements would remain locked in galactic centers, limiting the chemical evolution of the cosmos. Ultra-fast outflows may be nature's way of ensuring that metals don't remain confined, but instead spread outward to enrich the universe. The sheer variability of AGN activity over time adds another layer of complexity. Some galaxies exhibit signs of past outflows, fossil winds, where large-scale bubbles and cavities remain, but the AGN itself has gone dormant. These relics are detected via radio observations or soft X-ray imaging, revealing ghostly echoes of past violence. In other systems, we catch the AGN in mid-burst, witnessing the wind in real time as it accelerates and shapes the surrounding gas. These time-variable signals offer a glimpse into the life cycle of galactic cores, suggesting that black holes flicker on and off like cosmic engines rather than operating continuously. The link between ultra-fast outflows and galaxy morphology is becoming increasingly evident. Elliptical galaxies, especially massive ones, often show evidence of past outflow events, possibly the remnants of AGN-driven quenching that transformed once active, star-forming spirals into the dormant giants we see today. Meanwhile, galaxies in earlier stages of evolution, particularly those undergoing mergers, tend to host more active outflows. These systems provide natural laboratories for studying the feedback process in action, capturing AGN activity as it peaks and reshapes its host. In clusters of galaxies, the role of ultra-fast outflows becomes even more pronounced. Central galaxies and clusters often host powerful AGN, and their outflows can heat and stir the intracluster medium on scales of hundreds of kiloparsecs. This heating prevents the gas from cooling and condensing into stars, regulating not just the central galaxy but the entire cluster environment. The bubbles and cavities observed in the hot gas of galaxy clusters, often seen in radio and X-ray imaging, stand as testament to the power of AGN outflows to influence not just galaxies, but the vast structures in which they reside. Cosmic evolution models now include ultra-fast outflows as essential components of galaxy formation. Without them, simulations produce bloated, unrealistic galaxies with runaway star formation and overly massive bulges. By injecting energy into the system at critical times, outflows help sculpt galaxies into the forms we observe, reproducing the diversity of spirals, ellipticals, and dwarfs across the universe. This feedback not only tempers star formation but also maintains the correlation between black hole mass and galactic bulge mass, an empirical relationship that has puzzled astronomers for decades. From a philosophical standpoint, the idea that a single object, an invisible black hole, can govern the behavior of an entire galaxy is profound. Through its accretion-powered outflows, the black hole becomes a central architect of cosmic structure. It's no longer just a passive sinkhole in space, but an active participant in the story of galaxies. It shapes, regulates, and even sterilizes its surroundings, playing a role far beyond its gravitational pull. Ultra-fast outflows are the messengers of this influence, transmitting the black hole's authority across vast cosmic distances. The more we study these outflows, the more we realize they are not isolated curiosities, but universal phenomena. They appear in galaxies of many types, across all redshifts, from the local universe to the cosmic dawn. They represent one of the key levers by which galaxies evolve, and perhaps the clearest evidence that the universe is not governed solely by gravity, but by the intricate interplay of energy, momentum, and radiation. And within that intricate dance, ultra-fast outflows are among the most dramatic performers. Instruments like Chandra, XMM Newton, and New Star have enabled astronomers to detect the telltale blue shifted absorption lines in the X-ray spectra of active galaxies, clear signatures of gas moving toward us at immense speeds. These lines, often imprinted by highly ionized iron, Fe-XXV and Fe-XXVI, are some of the most direct tracers of ultra-fast outflows. By measuring their shifts and broadening, scientists can infer not just the velocity of the gas, but also its ionization state, column density, and even its location relative to the black hole. Each new observation adds another data point to the mosaic of understanding, allowing astrophysicists to model these outflows with increasing precision. The sheer diversity of ultra-fast outflows across different galaxies suggests that they are not rare anomalies, but rather integral stages in the life cycle of many, if not most, massive galaxies. Their presence in both nearby Seyfert galaxies and distant quasars implies a kind of universality, a consistent, underlying mechanism powered by accretion physics that transcends galactic type or cosmic era. This has massive implications for models of galaxy evolution, particularly the role of AGN in regulating star formation and shaping galactic morphology over billions of years. One of the more intriguing discoveries in recent years is the potential link between ultra-fast outflows and the coevolution of black holes and their host galaxies. There is a now well-established correlation between the mass of a galaxy's central black hole and the velocity dispersion of its stars, a relationship known as the M-sigma relation. This suggests that somehow, the black hole knows about the galaxy's overall dynamics, or vice versa. Ultra-fast outflows offer a mechanism for this connection. By injecting energy and momentum into the galaxy's bulge, these winds can regulate both the growth of the black hole and the formation of stars, maintaining a kind of equilibrium over cosmic time. But understanding how this feedback loop stabilizes is a major challenge. Simulations show that if outflows are too weak, they fail to halt star formation, allowing galaxies to grow too large and bright. If they're too strong, they blow away all the gas, leaving behind red, dead galaxies with no potential for rejuvenation. The key is balance, an ongoing tug-of-war between inflow and outflow, accretion and expulsion. Ultra-fast outflows are one of the primary players in this cosmic balancing act, and getting their parameters right is essential for any realistic model of galaxy formation. Beyond their impact on individual galaxies, these outflows may also contribute significantly to the enrichment of the intergalactic medium. As they escape the confines of their host galaxies, they carry with them metals, elements heavier than helium, that were forged in earlier generations of stars. These elements are then dispersed into the vast cosmic web, seeding future galaxies with the building blocks for planets, life, and new stars. Without such dispersal mechanisms, the universe would be a much duller place, composed mostly of hydrogen and helium. Ultra-fast outflows are, quite literally, spreading the ingredients of complexity across the cosmos. Interestingly, not all outflows are symmetrical. Many AGN-driven winds appear to favor certain directions, often aligned with the rotation axis of the accretion disk or the orientation of the host galaxy. This anisotropy can create large-scale structures like ionization cones, vast, funnel-shaped regions where radiation and particles escape more freely. These cones can extend for tens of thousands of light-years, illuminating surrounding gas clouds and leaving glowing fingerprints that astronomers can study in multiple wavelengths. Their presence hints at a dynamic, directional nature to AGN feedback, one that may vary dramatically depending on viewing angle and galactic geometry. Adding to the complexity is the fact that ultra-fast outflows often coexist with other types of AGN-driven phenomena, such as relativistic jets. In radio-loud galaxies, jets dominate the feedback landscape, drilling narrow beams of energy through the galactic environment. But even in these systems, ultra-fast outflows can exist alongside the jets, sometimes competing for dominance, sometimes acting in concert. The interaction between these two mechanisms is still not fully understood, but it's likely that each contributes to feedback in different ways, jets by piercing and heating large-scale structures, and outflows by broadly sweeping and stirring galactic material. The interplay between outflows and jets becomes even more critical when one considers the environments of galaxy clusters. In these dense cosmic ecosystems, galaxies are embedded in hot, X-ray-emitting gas known as the intracluster medium. Here, AGN feedback doesn't just affect individual galaxies, it can influence the temperature, density, and entropy of entire clusters. Some simulations suggest that repeated AGN outbursts, powered by both jets and outflows, can prevent runaway cooling in the cluster core, a process that would otherwise lead to excessive star formation. This heating, often referred to as maintenance mode feedback, is crucial for explaining the observed properties of galaxy clusters. The longevity of ultra-fast outflows is another open question. Do they persist only as long as the AGN is actively feeding, or can they continue even after the black hole enters a quiescent state? Some theories suggest that the momentum imparted to gas during the outburst phase is enough to sustain motion for millions of years, long after the core has gone quiet. In this sense, a single episode of high-energy activity could have ripple effects that last far longer than the outburst itself, shaping the future of the galaxy in profound ways. We are also beginning to learn that not all AGN are equal in their ability to produce these outflows. The mass of the black hole, the rate of accretion, the structure of the accretion disk, and the composition of the surrounding material all seem to influence whether an ultra-fast outflow will form, and how powerful it will be. Some AGN produce outflows with velocities topping 0.4 c, while others exhibit weaker, slower winds that barely escape the galactic core. Understanding the conditions that give rise to these differences is one of the frontiers of high-energy astrophysics. Ultra-fast outflows challenge our broader understanding of black holes themselves. Far from being passive consumers of matter, black holes appear to be active agents of cosmic change. They convert gravitational energy into vast waves of momentum and heat, sculpting galaxies and enriching the universe. These winds are not just side effects of accretion, they are fundamental to the story of how galaxies live, evolve, and eventually die. In tracing their origins and consequences, we are also tracing the grand architecture of the cosmos itself. A relationship known as the M-sigma relation, which suggests that black holes and galaxies grow in tandem. But how does a tiny, dense singularity influence an entire galaxy thousands of light-years across? Ultra-fast outflows may be the answer. These winds, though launched from a relatively small region around the black hole, carry with them enough kinetic energy to impact the galactic bulge on large scales. Over time, the accumulation of outflow episodes may regulate both the growth of the black hole and the star formation rate, maintaining a kind of cosmic balance that preserves the M-sigma correlation across cosmic time. But the influence of ultra-fast outflows doesn't end at the edges of galaxies. In powerful AGN, especially quasars, these outflows can punch through the galactic halo and into the intergalactic medium. There, they can enrich the surrounding environment with heavy elements, iron, silicon, carbon, that were forged in stars and recycled through the AGN. This chemical seeding is crucial for the evolution of the cosmic web. It means that even the seemingly empty voids between galaxies bear the fingerprints of AGN activity, evidence of the far-reaching arms of black hole influence. The detailed structure of these outflows is a subject of intense study. Are they smooth and continuous like a steady wind, or are they clumpy and chaotic, filled with pockets of dense gas embedded in lower-density plasma? High-resolution simulations suggest the latter may be more accurate. These clumps could be critical in explaining the observed variability in absorption lines, flickers in the X-ray spectra that occur as different portions of the wind pass in and out of our line of sight. If the outflows are indeed clumpy, they might be more resilient, able to maintain their velocity and structure even in the face of surrounding turbulence. Another complexity is how the outflows interact with the galaxy's magnetic fields. Galaxies are not just neutral matter, they are threaded with magnetic lines that shape everything from star formation to spiral arm structure. When ultra-fast outflows collide with these magnetic fields, they may twist or compress them, generating localized magnetic storms. These interactions could induce secondary effects, such as additional heating of the galactic gas or the generation of cosmic rays. Understanding these interactions will likely require a combination of deep observations and advanced magnetohydrodynamic simulations that can capture the behavior of both particles and fields. It's also important to consider the role of angle, where we are observing the galaxy from. Some AGN appear more luminous or show different spectral signatures simply because we are viewing the accretion disk edge-on or face-on. Ultra-fast outflows may be anisotropic, launching preferentially along certain angles or shaped by surrounding toroidal gas structures. This geometry affects what we can see and can bias our understanding of how common and powerful these outflows really are. Only by collecting data from a wide variety of angles and distances can astronomers build a statistically robust picture of these flows across the universe. Emerging instruments, such as the upcoming Athena X-ray Observatory and the LYNX mission concept, are expected to revolutionize our understanding of these phenomena. With greater sensitivity and spectral resolution, they will be able to detect fainter outflows and more distant galaxies, resolving the inner workings of AGN with unprecedented clarity. These instruments will help answer lingering questions. What triggers the start of an ultra-fast outflow? How long do they last? And how do their properties vary with the mass of the black hole or the richness of the surrounding environment? In parallel, time-domain astronomy is beginning to shed light on the variability of AGN and their associated winds. With long-term monitoring, astronomers have begun to notice that outflows can switch on and off over timescales of months to years. These transitions are not always gradual. Some are sudden, as if the central engine experienced a dramatic change in its accretion rate. Such fluctuations could result from instabilities in the accretion disk, interactions with infalling material, or the influence of a binary black hole companion. Each scenario offers new insights into the rich and unpredictable life of active galaxies. At cosmological scales, ultra-fast outflows could be a major driver of the so-called downsizing effect, where the most massive galaxies stop forming stars earlier than their smaller counterparts. The theory suggests that AGN in large galaxies eject or heat their gas reservoirs more efficiently, starving them of the raw material needed for star formation. Observations of high-redshift quasars with intense outflows support this idea, showing evidence that powerful winds can quench star formation even when the universe was only a few billion years old. These early shutdowns have lasting impacts on the galaxy's color, shape, and future evolution. The link between ultra-fast outflows and galaxy color is another emerging area of research. Galaxies are often classified as blue-green or red, corresponding to their star formation activity. Blue galaxies are actively forming stars, red galaxies are passive and dead, and green galaxies are in transition. Many AGN-hosting galaxies fall in this green valley, suggesting that their central activity might be responsible for halting star formation. Ultra-fast outflows could be the mechanism that nudges galaxies from blue to red, stripping or heating their gas and forcing them into senescence. Yet not all AGN outflows are destructive. Some may be constructive, compressing gas clouds just enough to trigger new waves of star formation. These so-called positive feedback cases are rare but significant, offering a counterpoint to the dominant quenching narrative. In certain galaxies, like some compact starbursts or luminous infrared galaxies, AGN winds may coexist with intense star formation. Understanding the balance between triggering and suppressing effects is one of the field's most exciting frontiers, as it challenges the simplistic view of AGN as purely negative forces in galactic ecosystems. The complexity deepens further when considering multiphase outflows, those that include not just hot ionized gas, but also warm neutral gas, cold molecular gas, and even dust. Recent studies using ALMA, the ATACMS, a large millimeter/submillimeter array, have detected fast-moving molecular gas in several AGN, implying that even the densest, coldest material can be swept up by ultra-fast outflows. This is remarkable because molecular gas is the direct fuel for star formation. The presence of this phase in outflows signals a more efficient suppression mechanism than previously thought and expands the scope of AGN feedback into new thermal regimes. The cumulative effects of ultra-fast outflows may shape not just galaxies, but clusters of galaxies. In large-scale environments like galaxy clusters, AGN outflows can inflate enormous bubbles in the intracluster medium, giant cavities visible in X-rays that extend for hundreds of thousands of light-years. These bubbles rise buoyantly, transporting energy outward and preventing catastrophic cooling flows that would otherwise trigger uncontrolled starbursts in the cluster core. In this way, a single AGN can regulate the temperature of an entire cluster, demonstrating the astonishing reach and influence of these enigmatic, ultra-fast winds. Of the line of sight. These fluctuations are like fingerprints of a turbulent, multi-phase wind, evidence of shock fronts, magnetized structures, and chaotic eddies in the outflow. Each time a dense clump crosses the X-ray beam from the AGN, it leaves an imprint, giving astronomers clues about the internal anatomy of the wind. This turbulence adds complexity, but it also allows for the possibility of mixed-temperature gas, which affects how the wind interacts with the surrounding interstellar medium and what kind of feedback it delivers to the host galaxy. Radiation pressure is often cited as the primary driver of these ultra-fast outflows, but the details are anything but simple. When an AGN shines with immense luminosity, its radiation exerts a force on the gas through Thomson scattering and resonance line absorption. If the force of this radiation exceeds the gravitational pull of the black hole, it can launch gas outward at incredible speeds. However, once the gas becomes highly ionized, as it often does in the vicinity of an AGN, it becomes more transparent to radiation, reducing the effectiveness of radiation pressure. This leads researchers to explore hybrid models involving both radiation and magnetic fields to sustain acceleration. Magnetohydrodynamic (MHD) forces may play a vital role, particularly in the innermost regions of the accretion disk. Here, magnetic field lines can thread the disk like tightly coiled springs, storing vast amounts of energy. When these fields become unstable or twisted, they can release their energy explosively, launching gas in tightly collimated jets or wide-angle outflows. These MHD-driven winds may explain some of the highest velocity UFOs observed, which seem too powerful to be driven by radiation pressure alone. The geometry, launch radius, and density of the disk all contribute to how this magnetic energy is channeled into the wind. As these winds escape the gravitational influence of the black hole, they undergo dramatic transformations. They cool, decelerate, fragment, and mix with the ambient medium. Some components become invisible to X-ray detectors, hidden behind clouds of dust or diluted to the point where they blend with the background. Others retain their high-energy signatures, persisting as detectable outflows for thousands of years. The challenge for astronomers is to build a coherent picture of the full life cycle of these winds, from their birth near the black hole to their ultimate fate in the galactic outskirts, or beyond. In galaxy clusters, where thousands of galaxies interact within a shared gravitational envelope, ultra-fast outflows can even influence the larger intracluster medium. When several AGN erupt within a short time span, their collective outflows can create cavities, shock waves, and pressure differences in the hot plasma that fills the space between galaxies. This feedback loop can alter the cooling flow of gas onto galaxies, suppressing new star formation not just in one galaxy, but across entire clusters. It's a cosmic-scale ripple effect, initiated by compact engines billions of times smaller than the regions they ultimately affect. The energetics involved in these processes are staggering. A single ultra-fast outflow can carry kinetic power equivalent to billions of supernovae. In a powerful quasar, this outflow can reach several percent of the total luminosity of the AGN, which itself can outshine an entire galaxy. These numbers are not just astronomical in scale, they're transformative. They suggest that AGN outflows aren't just byproducts of black hole feeding, but rather intentional, self-regulating mechanisms built into the architecture of galaxy evolution. In distant quasars, where AGN activity was most intense during the early universe, ultra-fast outflows may have played an even more dominant role. At redshifts greater than 6, when the universe was less than 1 billion years old, quasars already hosted supermassive black holes with masses exceeding 1 billion suns. To grow so rapidly, these black holes must have consumed matter at a ferocious rate, and with such extreme accretion likely came powerful outflows. Studying these ancient UFOs is like peering into the infancy of the cosmos, uncovering how the first galaxies were shaped, sculpted, and sometimes stifled by their central black holes. However, detecting these distant outflows is far from easy. The light from ancient quasars has been redshifted by the expansion of the universe, moving key absorption lines out of the range of many X-ray telescopes. Moreover, the intervening intergalactic medium introduces absorption and noise, making the signal faint and difficult to interpret. To overcome this, astronomers use gravitational lensing, stacking techniques, and long-exposure observations to tease out the faint traces of ancient winds. Every confirmed detection pushes back the timeline for AGN feedback, showing that even in the first few 100 million years of cosmic history, black holes were already shaping galaxies. The presence of UFOs in both high and low luminosity AGN suggests a broad range of driving mechanisms. In some cases, radiation pressure dominates. In others, magnetic forces take the lead. This diversity raises a fundamental question: are all UFOs the same phenomenon observed under different conditions? Or are there multiple classes of AGN winds with distinct origins and evolutionary paths? Answering this question is key to constructing unified models that explain how black holes influence their host environments across all mass scales and epochs. The next generation of observatories may bring us closer to these answers. Missions like Athena, Advanced Telescope for High-Energy Astrophysics, LINX, and XRISM promise to provide unprecedented resolution in X-ray spectroscopy. With these instruments, astronomers hope to map the detailed kinematics, composition, and structure of UFOs in dozens or even hundreds of AGN. These observations will help clarify not just how fast the outflows move, but also how much mass they carry, where they originate, and how long they persist. Complementing these efforts, advances in computational astrophysics are allowing researchers to simulate AGN outflows at unprecedented fidelity. These simulations incorporate relativistic effects, magnetic turbulence, radiative transfer, and feedback on star formation, producing digital galaxies that evolve under the influence of realistic AGN winds. Comparing these simulations to observations is a crucial step in validating our models and refining our understanding of the role these extraordinary winds play in the cosmic story. Understanding the balance between radiation pressure and magnetic field influence is critical to solving one of the most complex puzzles about AGN: the mechanism that allows ultra-fast outflows to reach such staggering velocities. If radiation pressure alone can't push the gas beyond a certain speed because of overionization, then the only viable alternative is a magnetic mechanism. In this scenario, the wind is driven by magnetocentrifugal forces, with the gas sliding along magnetic field lines like beads on a wire. This concept, proposed in magnetically arrested disk (MAD) models, opens up new possibilities for how AGN regulate their surrounding environment. Some of the most extreme examples of ultra-fast outflows come from broad absorption line (BL) quasars. These are among the most luminous AGN known, and their outflows often reach speeds above 0.2 times the speed of light. The spectra of BL quasars display broad troughs where light has been absorbed by highly ionized elements like C4, and NV. These features are key indicators of outflows that cover a large fraction of the source, possibly enveloping it in a shell-like structure. Their breadth and depth give insights into the density, covering fraction, and geometry of the outflowing gas. As these outflows expand, they interact violently with the interstellar medium of their host galaxy. This interaction creates shock fronts, where the supersonic wind slams into slower-moving or stationary gas. The shock compresses the interstellar medium, heats it to high temperatures, and in some cases can trigger new waves of star formation. But if the energy deposited is too high, It can sweep away gas entirely, quenching the galaxy's ability to birth new stars. This duality, creation and destruction, lies at the heart of AGN feedback, and ultra-fast outflows are one of its most potent agents. Shock ionization is another effect that arises from these interactions. As the gas accelerates through the galactic environment, it emits radiation not only from its temperature but also from its ionization state. These emissions provide a wealth of diagnostic information. Observing the line ratios of certain forbidden transitions, like those of oxygen or neon, can tell astronomers about the temperature and density of the shocked gas. These are the fingerprints of past violence, etched into the spectral code of the galaxy's light. A crucial feature of ultra-fast outflows is their variability over time. Some AGN have been observed to switch states, going from phases with strong outflows to periods of quietude and back again. This suggests that the outflows are not steady winds but episodic, possibly tied to instabilities in the accretion disk or changes in black hole feeding rates. This variability challenges the assumption that feedback from AGN is continuous. Instead, it points to a pulsed, dynamic system where black holes breathe in and exhale matter in dramatic bursts. The influence of these outflows on galaxy evolution can be profound. In massive elliptical galaxies, where star formation has ceased, the signatures of past AGN activity remain imprinted in their hot halos and X-ray emissions. These relics are reminders that ultra-fast outflows may have once swept through, clearing gas and halting star formation. This is known as negative feedback. But in some systems, especially those still forming stars, the energy from the outflows may compress gas clouds, leading to pockets of starburst activity, a form of positive feedback that paradoxically uses destruction to create. The ability to detect ultra-fast outflows depends heavily on our technological capability. Only with the most sensitive X-ray and ultraviolet observatories can we see the telltale blue-shifted absorption lines that betray their presence. Instruments like the Chandra X-ray Observatory and XMM Newton have made major contributions, but the next generation of space telescopes promises even deeper insights. Missions like XRISM and Athena will offer higher-resolution spectroscopy, potentially allowing astronomers to map the structure of outflows with unprecedented detail. At the heart of the analysis lies the ionization parameter, which is a key quantity that describes the state of the gas in an outflow. It depends on the intensity of the ionizing radiation and the density of the gas, forming a delicate interplay that determines which ions can exist in the wind. By modeling the ionization parameter, astronomers can reconstruct the physical conditions of the outflow, deduce its composition, and estimate its mass and velocity, all critical components for assessing the impact of AGN feedback. One of the most promising avenues of study is time-resolved spectroscopy, where the changes in absorption features are tracked over time. This can reveal how outflows evolve, how quickly they respond to changes in the accretion rate, and whether they are launched in phases or in a continuous stream. These observations may eventually lead to a kind of weather forecasting for AGN, where we can predict the onset of powerful winds based on prior fluctuations in their light curves or emissions. Another topic of major interest is the role of black hole spin in powering ultra-fast outflows. According to the Blandford's-Nagic mechanism, a rapidly spinning black hole can transfer energy from its rotation into magnetic fields, which in turn can launch jets and possibly contribute to the power of outflows. Measuring black hole spin is challenging, but correlations between spin and outflow power could provide new evidence for this connection, deepening our understanding of how these cosmic engines function. Further complexity arises when we consider that some AGN have both ultra-fast outflows and relativistic jets. These are different phenomena but may originate from similar regions near the black hole. How they coexist, interact, or suppress each other remains an open question. Some theories suggest that when a black hole is in a high accretion state, it favors winds over jets, and vice versa. Understanding this dichotomy could be key to unraveling the evolutionary path of galaxies over billions of years. In environments where multiple AGN outflows from different galaxies converge, such as in galaxy clusters, their collective effect can reshape the intergalactic medium itself. These outflows, enriched with metals and energy, may contribute to the heating of intracluster gas, suppress cooling flows, and influence the large-scale structure of the universe. In this sense, ultra-fast outflows are not isolated events, but components of a larger, interconnected cosmic ecosystem. Ultra-fast outflows have the extraordinary power to shape galaxies, but their impact depends entirely on how much energy they carry. When the energy transferred to the surrounding gas is immense, it can disrupt the cold molecular clouds that form stars. Instead of helping stars ignite, the outflow can blow away the star-forming material, halting future stellar births. In these cases, the AGN acts like a galactic extinguisher, quenching the potential of an entire galaxy and accelerating its evolutionary decline into a red, dead system. On the other hand, there are scenarios where the outflow's shockwaves compress ambient gas, triggering bursts of star formation. It becomes a paradoxical engine, destroying in some regions while creating in others. This phenomenon, often referred to as positive feedback, hints at a complex relationship between the central black hole and its host galaxy. Rather than simply being destructive, ultra-fast outflows could be architects of the very systems they seem to tear apart, acting with both surgical precision and brute force across cosmic scales. Beyond the boundaries of galaxies, these outflows don't just disappear, they become messengers. Carrying with them heavy elements like carbon, oxygen, and iron, the outflows inject chemically enriched gas into the intergalactic medium. These metals were forged in ancient stars, and now, through the violence of an AGN outflow, they are redistributed into the wider universe. This process helps explain why even the most remote corners of the cosmos show traces of complex elements, even in regions far removed from any galaxy. The geometric complexity of ultra-fast outflows presents a unique challenge for astrophysicists. Unlike a laser beam or a radial explosion, these winds can bend, split, or take on hollow cone shapes depending on the forces at play. In some cases, they are tightly focused, resembling narrow jets, while in others, they spray outward in wide angles. Even within a single AGN, the structure of the outflow can vary over time as the accretion disk fluctuates, or as magnetic fields shift. This variability makes modeling and observation a constantly evolving pursuit. Instruments like the European Space Agency's XMM Newton and NASA's Chandra X-ray Observatory have been indispensable in detecting the fingerprints of these outflows. By analyzing absorption features in the X-ray spectra, scientists can determine how fast the gas is moving, what elements are present, and how dense the outflow is. In some cases, astronomers can even detect multiple layers of outflows, like nested shells, each moving at different velocities and showing different compositions, like an onion of cosmic wind peeling itself across space. Computer simulations are crucial in helping theorists understand how these outflows behave under various physical conditions. By tweaking magnetic field strengths, black hole masses, accretion rates, and environmental densities, researchers can recreate the complex interactions seen in actual AGNs. These models help explain why some outflows are strong enough to blow gas entirely out of a galaxy, while others stall closer to the core, unable to escape the gravitational pull of the central supermassive black hole. Perhaps one of the most exciting possibilities is the connection between ultra-fast outflows and the growth regulation of black holes themselves. When gas spirals toward a supermassive black hole, it heats up and emits radiation, but it also feeds the black hole's mass. If outflows are strong enough, they can clear away this infalling material, effectively cutting off the black hole's food supply. This self-regulating feedback loop could be nature's way of preventing black holes from growing without bounds, a cosmic control mechanism baked into the very structure of galaxy formation. There's also increasing evidence that ultra-fast outflows might play a role in shaping the cosmic web. As they expel energy and mass into the intergalactic medium, they help define the boundaries between voids and filaments. Over billions of years, this redistribution of matter contributes to the large-scale structure of the universe. AGN outflows, once thought to be purely local phenomena, may therefore have implications on the grandest scales imaginable, influencing the clustering and evolution of galaxies on a cosmological level. The detection of ultra-fast outflows at high redshifts, distances so vast we are looking billions of years into the past, suggests that these winds have been present since the early universe. Some of the earliest quasars, which formed less than 1 billion years after the Big Bang, already show signs of powerful winds ejecting material at relativistic speeds. This hints that outflows have been a fundamental component of galaxy evolution from the very beginning, not a late-stage phenomenon. Their presence at such early epochs challenges existing models and suggests that feedback mechanisms have been shaping the universe since its infancy. One of the most mind-bending discoveries is the evidence that ultra-fast outflows may influence not just star formation and black hole growth, but even dark matter distribution. If an AGN outflow is powerful enough to change the gravitational potential of a galaxy, it could perturb the dark matter halo that surrounds it. While dark matter doesn't interact with radiation or magnetic fields, it does respond to changes in gravity. Therefore, a strong enough outflow might subtly reshape the dark skeleton of a galaxy, leaving a fingerprint not just in baryonic matter, but in the invisible architecture beneath. Some of the most promising future observatories, like the Athena X-ray Observatory and the Lynx mission, aim to study ultra-fast outflows with unprecedented resolution. These telescopes will be able to track the movement of individual gas clouds across time, resolve spectral lines with far more precision, and detect fainter outflows in galaxies that were previously too distant or dim. This technological leap will allow astrophysicists to build a more complete timeline of how AGN outflows evolve and interact with their environments across billions of years. All of this research is slowly revealing a profound truth. Ultra-fast outflows are not mere byproducts of galactic activity. They are central agents in the cosmic story. They bridge the small-scale drama of black hole feeding with the large-scale architecture of the universe. They sculpt galaxies, seed the cosmos with metals, regulate star formation, and possibly even influence dark matter structures. As our instruments sharpen and our simulations grow more detailed, we edge closer to understanding these colossal winds, not as anomalies, but as the heartbeat of the evolving universe. The geometric complexity of ultra-fast outflows is one of the reasons they remain so difficult to model. These outflows are not uniform streams. They can be broad cones, narrow jets, or diffuse bubbles expanding outward at different angles. The shape and direction of each outflow depend on the internal structure of the AGN, the configuration of the magnetic fields, and the density of the surrounding gas. In many cases, simulations reveal highly chaotic flows that bend, fork, and even loop back into the galaxy, creating shockwaves and turbulence along the way. This chaotic nature adds layers of difficulty to observing them directly. Most of our information about ultra-fast outflows comes from studying the absorption lines in the X-ray and UV spectra of AGN. These lines act like fingerprints left behind by the gas racing away from the central black hole. By examining the depth, shift, and shape of these lines, scientists can estimate the velocity, composition, and density of the outflowing material. But interpreting this data is a puzzle in itself, often requiring complex models to separate the outflow's signature from the background noise of the galaxy. Sometimes, the outflows interact violently with other material around the AGN. Dense clumps of gas can create bow shocks when struck by the outflow, causing the gas to light up in specific wavelengths. These emissions provide another way to trace the path of the outflow through the host galaxy. The results can be spectacular: bright arcs, filaments, and bubbles appearing in X-ray or radio maps, offering a snapshot of the energy being deposited into the galactic environment at that very moment. Yet, even with all our tools, there is still much we don't understand. For instance, why are some AGNs accompanied by extremely powerful outflows while others, just as massive, show almost no sign of them? What triggers the launch of these ultra-fast winds, and what governs their lifetime? Are they continuous, or do they come in episodic bursts, like cosmic cannon fire? These questions suggest that our understanding of the relationship between black holes and galaxies is far from complete. Computer simulations have started to shed light on these dynamics. Advanced models that include magnetohydrodynamics and radiation transfer are helping researchers understand how the outflows originate from the accretion disk and how they evolve over time. These simulations often reveal a feedback loop. The outflow affects the galaxy, which in turn changes the conditions around the black hole, influencing future outflows. It's a delicate cosmic ballet of cause and effect, stretching across millions of years. Some simulations also suggest that ultra-fast outflows could play a role in galaxy mergers. When two galaxies collide, their central black holes may eventually merge as well. But before that happens, the outflows from each AGN can interact, either reinforcing or canceling each other out. The resulting turbulence can be extreme, injecting even more energy into the surrounding gas and potentially accelerating the merger process. This could help explain why some post-merger galaxies exhibit both signs of starburst activity and rapid AGN-driven feedback. In some cases, the outflows can be so powerful that they escape the gravitational pull of not just the galaxy, but the entire dark matter halo surrounding it. When that happens, the material is essentially lost to intergalactic space forever. This leads to a kind of galactic bleeding, where essential gas is removed permanently, reducing the galaxy's long-term ability to form stars or evolve. It's like an open wound. Once the gas is gone, recovery becomes nearly impossible. Astronomers have identified outflows with speeds exceeding 0.3 times the speed of light, nearly 90,000 kilometers per second. At these incredible velocities, the outflows don't just reshape the galaxy, they rewrite its history. The time it takes for such gas to cross the galaxy can be as short as a few 100,000 years, which is incredibly brief on cosmic timescales. In that time, the outflow can sterilize star-forming regions, collapse molecular clouds, and even trigger secondary flows in the opposite direction. There is growing evidence that these outflows may also be connected to the large-scale structure of the universe. Some studies suggest that outflows can travel far enough to influence the behavior of nearby galaxies, especially those that lie along the same cosmic filament. In this way, ultra-fast outflows could be a mechanism for long-range galactic interaction, far beyond the reach of gravity alone. This would make them not just local influencers, but players in the architecture of the cosmic web itself. Instruments like the Chandra X-ray Observatory, XMM Newton, and ALMA have been instrumental in detecting these powerful outflows. By observing AGNs at different wavelengths, X-ray, UV, optical, and radio, astronomers are building a more complete picture of how the outflows behave across different environments. Each wavelength tells a different part of the story. X-rays reveal the hottest gas, UV exposes high-speed ionized winds, and radio maps the magnetic fields guiding the flow. Some of the most powerful outflows have been observed in quasars, extremely luminous AGNs located billions of light-years away. Despite their distance, the outflows they produce are so energetic that we can measure their effects with precision. These distant beacons allow us to peer into the ancient universe and study how the first galaxies evolved under the influence of supermassive black holes. In some cases, the outflows are so vast they stretch across hundreds of thousands of light-years, enveloping entire galactic clusters in their influence. The scale of these phenomena is staggering, but what's even more astounding is that we're just beginning to grasp their importance. The deeper we study them, the more it becomes clear, ultra-fast outflows are not rare anomalies. They are central to how the universe evolves. They shape galaxies, seed intergalactic space, influence cosmic structure, and tie together the fates of black holes and stars in ways we are only beginning to understand. Yet, even with all our technological advancements, we are only beginning to understand the long-term consequences of ultra-fast outflows. What happens to a galaxy millions of years after it's been struck by such a violent force? Does it recover and resume star formation, or does it quietly fade into dormancy? Astronomers use powerful simulations to extend their understanding across cosmic time, and these models suggest that AGN feedback, especially from outflows, plays a crucial role in the life cycles of galaxies, determining when they shine and when they dim forever. Some galaxies seem to wear the scars of these outflows. Elliptical galaxies, which are often older and redder, show signs of having undergone dramatic quenching in their past. Their gas reservoirs are depleted, their star-forming regions are silent, and their cores are filled with the echoes of long-dead activity. Many scientists believe these galaxies once hosted extremely active AGN that launched ultra-fast outflows strong enough to evacuate the gas that once fueled star formation. These outflows, in effect, rewrote the destiny of an entire galaxy in just a few million years. Meanwhile, other galaxies demonstrate the opposite, an ongoing dance between the AGN and starburst regions. In these galaxies, the outflow doesn't suppress star formation, it seems to reshape it. The jets and winds stir the interstellar medium like a spoon in soup, creating eddies and waves that lead to the compression of gas clouds. Where this compression is just right, stars are born. So, while one part of the galaxy may be dimming under the AGN's wrath, another part may be igniting with youthful, brilliant light. What makes ultra-fast outflows even more intriguing is their apparent universality. They have been detected not just in massive elliptical galaxies with supermassive black holes billions of times the Sun's mass, but also in smaller, younger galaxies with comparatively modest central engines. This suggests that the mechanics behind these outflows are not reserved for the cosmic elite. Rather, they may be a natural phase in the evolution of many, perhaps most, galaxies. The question then becomes, how early in the universe did these outflows begin shaping galactic evolution? Observations of high redshift quasars, those that existed when the universe was just a fraction of its current age, indicate that ultra-fast outflows were active even in the cosmic dawn. These early outflows could have had a disproportionate impact, given the smaller size and more chaotic nature of early galaxies. The feedback they delivered may have accelerated the transition from primeval gas clouds to structured galaxies filled with stars, dust, and complexity. One possibility being explored is that these outflows help prevent early galaxies from growing too fast. In a young universe flush with cold gas, unchecked star formation would rapidly exhaust the raw materials needed to form future generations of stars. But an AGN-powered outflow, erupting at just the right moment, could sweep out much of the gas and pause star formation, allowing a more measured evolutionary path. This self-regulation mechanism could explain the striking consistency observed in galaxy populations across different epochs. There is also growing evidence that ultra-fast outflows are not just solitary phenomena but can synchronize with larger cosmic structures. In clusters of galaxies, outflows from multiple AGN can interact, overlap, and even trigger chain reactions that reverberate across millions of light-years. These interactions create enormous cavities in the hot intracluster gas, giant voids carved out by repeated AGN eruptions. Some of these cavities are filled with relativistic particles, forming vast radio lobes that glow like ghosts of ancient explosions. The connection between these large-scale structures and their small-scale origins is a key focus of modern astrophysics. Researchers aim to understand how the energy output of a compact black hole, barely the size of our solar system, can ripple outward to affect galactic halos, intergalactic gas, and the very architecture of the universe. It's like throwing a pebble into a pond and watching the ripples reshape the shoreline. Only this pebble is a black hole, and the pond is billions of light-years wide. Not all outflows are the same. Some are purely radiative, driven by the intense light pressure of the AGN's accretion disk. Others are magnetically powered, launched by twisted magnetic fields coiled around the spinning black hole. There are also thermally driven outflows, which rely on extreme heat to expand and expel gas. Each of these mechanisms produces a different signature, velocity, and structure. By studying a wide variety of galaxies and AGN types, astronomers can piece together how these different outflows evolve and dominate under specific conditions. At times, ultra-fast outflows seem almost too powerful for their environments. They can punch holes through the interstellar medium, strip satellite galaxies of their gas, and even disrupt dark matter distributions. In these instances, the black hole at the center of the galaxy is no longer just a passive resident, it becomes a ruler, reshaping the galaxy's fate with every violent exhalation. These are not isolated cosmic storms, they are commanding events that echo through time and space. Understanding these outflows also has implications for the search for life elsewhere. If an AGN outflow passes through a region dense with planets or protoplanetary disks, it could strip atmospheres, sterilize surfaces, or disrupt planetary formation entirely. Conversely, in more benign forms, the heavy elements they disperse may seed future solar systems with the necessary ingredients for life. So even in the distant past, these outflows may have unknowingly influenced where life could, or could not, emerge. As our instruments become more sensitive, the curtain is slowly lifting. With telescopes like the James Webb Space Telescope and the next-generation X-ray observatories, we are poised to see these outflows not just as abstract concepts but as real, observable engines of cosmic change. The more we study them, the more it becomes clear, ultra-fast outflows are not side effects. They are central players in the epic drama of the universe. So, while one part of the galaxy may be dimming under the AGN's wrath, another part may be igniting in a frenzy of new stars. This duality is what makes ultra-fast outflows so compelling. They are not merely destructive or creative, but a mixture of both. They play a critical role in the regulation of galactic ecosystems, operating like a thermostat that prevents galaxies from growing uncontrollably while also ensuring they don't die too quickly. The balance they create might be essential for the long-term habitability of the universe as we know it. The question then arises, how common are ultra-fast outflows across the cosmos? Observational data suggests they are not rare. In fact, a significant fraction of luminous AGN exhibits signs of these rapid winds. The exact fraction depends on the sensitivity of our instruments and the angles from which we observe, but it's estimated that at least 30 to 40% of AGNs display outflow features detectable in X-rays. This implies that these phenomena are not anomalies. They're widespread, potentially universal features of active galaxies. But ultra-fast outflows do not always announce themselves loudly. Some can be cloaked by surrounding gas and dust, making them nearly invisible in traditional wavelengths. In such cases, only through indirect signatures, like asymmetrical emission lines, or anomalous motion in cold gas clouds, can we infer their presence. This hidden population suggests that we may be underestimating how influential and frequent these events truly are. Much like dark matter, their effects are felt more than seen. Recent advances in computational astrophysics have helped peel back the layers of these mysterious forces. By simulating entire galaxies with embedded AGNs, researchers can observe how ultra-fast outflows evolve over hundreds of millions of years. These simulations reveal that the shape and reach of the outflows depend heavily on the density gradients of the surrounding medium. In denser galaxies, outflows tend to get choked and trapped near the core. In lighter environments, they burst outward, carving channels through the interstellar and intergalactic medium. This interaction with the host galaxy's environment can also determine the effectiveness of feedback. If the outflow can escape easily, it carries its energy far from the center, influencing star formation across the galactic halo and beyond. If it is confined, the energy builds up in the nucleus, potentially triggering local bursts of star formation or violent eruptions. Either way, the black hole exerts a far-reaching influence, controlling structures light years beyond its gravitational grasp. Another fascinating aspect lies in the chemical fingerprints of these outflows. The winds carry not only energy but also enriched materials from the core of the galaxy. Spectroscopic analysis has revealed that these winds often contain metals formed in the hearts of stars, like iron, neon, and magnesium. The fact that these elements are observed in distant galactic halos and even the intergalactic medium suggests that ultra-fast outflows are among the primary distributors of heavy elements across cosmic distances. Some theories suggest that ultra-fast outflows may have helped shape the early universe in fundamental ways. During the epoch of reionization, when the first stars and galaxies were forming, outflows from primordial AGNs may have accelerated the heating and ionization of the intergalactic medium. This process could have cleared out the dense hydrogen fog that once filled the universe, allowing light to travel freely and structure to form more efficiently. The velocity of these outflows, often reaching 10% to 30% of the speed of light, gives them the power to punch through even the densest galactic environments. At such speeds, the outflowing gas becomes highly relativistic, meaning its mass, momentum, and energy behave differently from classical expectations. These conditions challenge traditional physics and require the inclusion of Einstein's relativistic equations to accurately model how the gas evolves and interacts with its surroundings. Despite their speed and power, ultra-fast outflows are surprisingly fragile. Turbulence, magnetic fields, and inhomogeneities in the gas can cause the outflow to fragment into clumps or filaments. Once fragmented, the energy is no longer distributed evenly, and the outflow may lose its coherence. This transition, from a focused, high-energy stream into a chaotic, dispersed flow, may be responsible for the diverse ways we observe AGN feedback across different galaxies. Researchers are now trying to connect ultra-fast outflows to other large-scale cosmic structures. For example, giant radial lobes observed in some active galaxies may be the fossil remains of long-dead outflows. Similarly, the enormous bubbles seen in the Milky Way, such as the Fermi bubbles, might be the aftermath of a past episode of nuclear activity and outflow from our own supermassive black hole. If true, it would mean that even relatively quiet galaxies like ours can carry the legacy of ancient ultra-fast outflows. In the coming decades, observatories like the James Webb Space Telescope and next-generation X-ray missions like Athena are expected to revolutionize our understanding of these phenomena. With greater resolution and sensitivity, astronomers will be able to peer deeper into galactic cores, resolve the fine structures of outflows, and track their motion over time. These tools will help answer pressing questions. How do outflows start? How do they end? And what determines their fate? The deeper we explore, the more it becomes clear that ultra-fast outflows are not simply cosmic windstorms. They are fundamental processes that help write the history of galaxies. Their role in regulating matter, shaping structure, and transporting energy across the universe places them at the very heart of cosmic evolution. What once appeared as strange disturbances around active galactic nuclei are now recognized as key drivers of the very architecture of the cosmos. Recent advances in computational astrophysics have helped peel back the layers of these mysterious forces, revealing how ultra-fast outflows evolve over time and interact with their host galaxies. Supercomputers running detailed simulations can now model the turbulent interaction between the outflows and the multi-phase interstellar medium. These simulations show shock fronts rippling outward, heating gas to millions of degrees, compressing dust lanes, and even altering the chemical composition of the galaxy. By tracking these changes over tens of millions of years, researchers gain insight into the complex feedback mechanisms shaping galactic evolution. In these virtual galaxies, scientists can test how different variables affect the behavior of ultra-fast outflows. They can increase the black hole's mass, change the accretion rate, or vary the density of surrounding gas. Each scenario reveals new facets of how energy and matter move on interstellar and intergalactic scales. For instance, when outflows strike dense molecular clouds, they can trigger collapse and star formation. But in lower density regions, they often push the gas outward, depleting the raw material needed for stellar birth. This dual outcome once again underscores the dynamic role outflows play in galactic ecology. Observations from ALMA, the Atacama Large Millimeter/Submillimeter Array, have confirmed some of these theoretical predictions. Astronomers have detected massive outflows of molecular gas being driven from galactic centers at extraordinary speeds, sometimes over 1,000 kilometers per second. These cold, dense gas flows are particularly intriguing because they are the very material needed for future star formation. If ultra-fast outflows are removing this fuel, they are essentially extinguishing the galaxy's future before it can unfold. Yet, the situation becomes even more fascinating when we consider the scale. Some outflows don't just affect their host galaxies, they reach into intergalactic space, spilling energy and particles across tens or even hundreds of thousands of light years. This redistribution of mass and momentum might contribute to the heating and enrichment of the intergalactic medium. Heavy elements like carbon, oxygen, and iron, which are forged in stellar interiors and scattered during supernovae, can be pushed out by AGN winds, helping to seed the cosmic web with the ingredients of future stars and planets. This cosmological recycling suggests that ultra-fast outflows are not merely a mechanism of galactic regulation, they are also agents of cosmic connectivity. They may help distribute the building blocks of life throughout the universe, long before any solar system or biosphere forms. It's a poetic thought that the violent winds of a ravenous black hole could, in some way, be responsible for the eventual emergence of life in a quiet, distant corner of the cosmos. Another intriguing discovery is the apparent relationship between ultra-fast outflows and the mass of their parent black holes. It appears that the most massive black holes tend to drive the most energetic winds. This correlation makes sense in the context of gravitational power, larger black holes can accumulate more matter, and therefore generate more intense radiation pressure. But the relationship is not linear, suggesting that other factors, such as magnetic fields, spin rate, and the structure of the accretion disk, may also play a pivotal role in outflow generation. Polarization studies, which analyze the orientation of electromagnetic waves, have added yet another layer of understanding. These studies reveal the geometry of the outflow and help determine whether we are seeing a wide-angle wind or a tightly collimated jet. In many cases, the data suggests that the ultra-fast outflows are not simple, symmetrical blasts. Instead, they are complex, layered structures with both high-density cores and more diffuse edges. This complexity makes modeling and predicting their impact on galaxies all the more challenging. X-ray spectroscopy remains one of the most powerful tools for studying ultra-fast outflows. When these outflows pass in front of the hot corona around the black hole, they absorb specific energies of X-ray light, leaving behind telltale absorption lines. The depth, width, and shift of these lines provide clues about the speed, density, and composition of the wind. Missions like Chandra and XMM Newton have cataloged dozens of such systems, providing a treasure trove of data for theorists and observers alike. The sheer energy involved in these outflows is almost incomprehensible. Some ultra-fast outflows carry enough power to equal the total energy output of billions of stars. When such forces are unleashed over a small region of space, the consequences are dramatic. Gas is stripped from galactic centers, magnetic fields are twisted and tangled, and shock waves ripple outward like cosmic tsunamis. It is in these environments that we see nature operating at its most extreme, where the rules of everyday physics are stretched to their limits. At the heart of this all is the supermassive black hole, a paradoxical engine that consumes matter while simultaneously powering some of the most energetic phenomena in the universe. The accretion disk, that luminous ring of infalling material, acts as both the fuel tank and the control panel for these cosmic outbursts. As matter spirals inward, it heats to millions of degrees, releasing X-rays and gamma rays that can accelerate winds to relativistic speeds. The result is an environment of violent extremes, radiation, gravity, velocity, all playing out in a region smaller than our solar system. And still, many questions remain unanswered. What determines whether an AGN will develop ultra-fast outflows or more gentle breezes? Why do some outflows quench star formation, while others stimulate it? Could we one day use these forces to understand galaxy formation on a universal scale, or even manipulate them in the distant future for galactic-scale engineering? These questions may sound like science fiction today, but the rapid pace of discovery reminds us that today's mysteries often become tomorrow's knowledge. Perhaps most exciting is the realization that every ultra-fast outflow we detect is a message from the past, a snapshot of galactic evolution frozen in time and hurled across the cosmos at the speed of light. By decoding these signals, we are not only learning about black holes and galaxies, but also about the history of our own cosmic neighborhood. And in that history, we may find the keys to understanding where we came from and where we're going. If ultra-fast outflows are removing this fuel, they are essentially extinguishing the galaxy's ability to produce new stars, a kind of slow-motion cosmic suffocation. This process, often called quenching, can transform once vibrant spiral galaxies into sterile elliptical ones, devoid of fresh stellar light. The timing of this process matters greatly. If it occurs too early, it can prevent the formation of complex structures like solar systems. If it happens too late, it can destabilize the galaxy. Ultra-fast outflows, therefore, don't just influence star formation, they determine the very fate of galaxies. Yet not all galaxies seem to suffer under the presence of these outflows. Some continue forming stars even while being bombarded by ultra-fast winds. In such cases, the orientation, strength, and scope of the outflows may allow certain regions of the galaxy to remain sheltered. This highlights the directional nature of these jets and winds. While devastating in one region, they may be entirely absent in another. This anisotropy complicates our efforts to generalize their effects across different types of galaxies, making each case a puzzle of its own. Another major implication of ultra-fast outflows lies in their role in redistributing elements. The material blasted away from galactic centers is often rich in heavy elements, metals like iron, oxygen, and silicon, that were forged in the hearts of massive stars and released during supernovae. When AGN-driven winds carry this enriched gas into the outskirts of the galaxy, or even beyond into the intergalactic medium, they effectively fertilize the cosmos. This is one of the primary methods by which the universe becomes chemically complex over time. We now suspect that many of the elements found in our own solar system, and perhaps even in our own bodies, may have once been part of such an outflow. Billions of years ago, as galaxies erupted with active black holes, their cores may have launched torrents of metal-rich gas into the void. Over time, some of that matter may have cooled, coalesced into new clouds, and eventually formed the very materials that built planets and life. In this way, ultra-fast outflows are not just agents of destruction, they are cosmic alchemists, seeding the universe with the ingredients for complexity. Instruments like NASA's Chandra X-ray Observatory and ESA's XMM Newton have been critical in detecting these outflows and analyzing their properties. By examining specific absorption lines in X-ray spectra, scientists can determine the speed, density, and composition of these winds. The blue-shifted iron K lines, in particular, have been a goldmine of information. These lines appear shifted toward shorter wavelengths, indicating that the absorbing material is racing toward us at tremendous velocities, sometimes up to 0.3 times the speed of light. One challenge, however, has been the intermittent nature of these signatures. Some AGNs show strong outflows at one time, only to appear dormant years later. This suggests that ultra-fast outflows may be episodic, turning on and off depending on the fueling state of the black hole. When material is readily available for accretion, the AGN ignites and launches powerful winds. But when the supply is cut off or thinned, the outflows cease, and the galaxy enters a quieter phase. These cycles of activity could repeat multiple times over a galaxy's lifetime. This episodic behavior adds a layer of complexity to galaxy modeling. To truly understand how ultra-fast outflows affect galactic evolution, we must not only observe their current state but also reconstruct their history. This has led to new efforts in time-domain astronomy, monitoring AGNs over long periods to catch them in various states of activity. Some of the most exciting discoveries have come from such persistent watching, revealing how quickly and dramatically a galaxy's core can change. Then there's the enigma of the driving mechanism itself. How do these winds get accelerated to such extreme velocities? The current leading theory involves radiation pressure from the AGN. As the accretion disk surrounding the black hole emits intense radiation, that energy pushes outward on the gas, propelling it away. However, not all radiation interacts equally with matter, and the exact coupling efficiency remains uncertain. Some researchers propose that magnetic forces, especially from twisted, rotating magnetic fields, may play a larger role than previously thought. This brings magnetohydrodynamics into the equation, where both the magnetic field and fluid dynamics of plasma must be considered. In such models, magnetic lines of force act like cosmic slingshots, flinging matter out at relativistic speeds. This could help explain the observed collimation of some outflows, where they appear more jet-like than wind-like. The combination of magnetic and radiative driving could be key to understanding the full range of ultra-fast outflow behavior across different AGNs. There are also deeper theoretical implications. If the black hole at the galaxy's center is spinning rapidly, that angular momentum could be transferred to the outflowing material via a process known as the Blandford's-Najek mechanism. This mechanism extracts energy directly from the rotating black hole's ergosphere through magnetic fields. If ultra-fast outflows are partially powered in this way, they may represent one of the few observational consequences of black hole spin, a property that remains notoriously difficult to measure directly. Ultimately, ultra-fast outflows sit at the intersection of several critical astrophysical domains: black hole physics, star formation, galactic dynamics, and cosmic chemical evolution. They are not side effects of AGN activity. They are central players in the story of how the universe grows, changes, and matures. And as we continue to probe their secrets, we are not just uncovering how galaxies work, we are revealing the forces that have shaped the very structure of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.